Welcome, curious minds and sleepy thinkers. You've found a soft place to land where the questions are big and the pace is slow enough not to jolt you out of your pillow cocoon. Tonight, we're going to tiptoe into one of the most mysterious chapters of our shared human story, a moment that echoed not just through the vastness of space, but through the delicate threads of our understanding of warfare and peace. It's a tale that forever changed how we perceive the heavens above and the fragile ground beneath our feet. But don't worry, we'll take it slow. This isn't a race through equations or a lecture on complex physics. It's more like floating through a galaxy of ideas with a cup of chamomile tea, allowing the thoughts to gently drift by like night clouds across the grand expanse of the sky, each cloud whispering a part of the story. Let your mind relax and listen to the soft echoes from the past lessons that still resonate with quiet urgency today. Let us drift slowly into this idea and cast our gaze back to the middle of the last century, an era marked by an unprecedented tension, a time when the world seemed to hold its breath with every subtle movement of two colossal powers. This was the Cold War, a struggle waged without overt battles or declared fronts, yet it held a silent, simmering power capable of reshaping the entire planet. It was not a conflict defined by clear battlefields or open aggression, but rather a quiet, psychological chess match, a profound test of wills between two opposing ideologies. In this silent contest, every gesture, every scientific leap was perceived as a message, a signal of strength and resolve. And among all the invisible arenas where this fierce competition played out, perhaps none expressed its intensity more vividly than the space race. It was not merely a contest of who could launch objects higher, further, or faster into the cosmic ballet. It was a majestic, unspoken performance where each rocket launch, each satellite successfully placed into orbit served as a profound declaration, an assertion of scientific prowess and military might. By the early 1960s, the atmosphere itself felt thick with anticipation and unease. This was a period of grand ambitions, yet it was also tinged with deep anxieties. The entire world watched, striving to decipher the subtle signals from across the ideological divide. The very first ripples of this cosmic competition had already begun to tremor through the air. Recall those nascent moments of this rivalry, the early Soviet triumphs that felt like gentle yet relentless waves steadily shifting the cosmic balance. When Sputnik 1 soared into the heavens in 1957, it was more than just a satellite. It was a persistent, rhythmic beep from the sky, an incessant reminder of Soviet technical capability. That faint, steady beep did not merely echo in the void. It resonated deeply within the minds of leaders and citizens across the globe. And then just 4 years later, when Yuri Gagarin became the first human to venture into that immense darkness beyond our atmosphere, his journey was a profound, almost spiritual moment for humanity. But in the context of the Cold War, it was also a powerful, almost unnerving statement. It affirmed a terrifying capability, a mastery over the heavens that sent shivers through the spines of those on the other side. This single orbital flight underscored a chilling reality. If a nation could send a human into space, what else could it send? What kind of unseen power might be orbiting silently, above, poised to alter the very fabric of global stability? The pressure on the United States intensified with each Soviet achievement. It was a quiet, relentless weight, pressing down on the nation's sense of security and its pride. A palpable fear began to take root that the Soviets might not just explore space, but might militarize it first. The thought of a potential adversary establishing a strategic foothold above the Earth, perhaps with capabilities unknown and terrifying, was a haunting specter in the strategic halls of Washington. This was not merely about prestige, it was about survival. Imagine the weight of that fear, the quiet conversations in hushed rooms, contemplating a future where the enemy could possess an ultimate high ground, a vantage point from which to exert unprecedented influence, or even dare we consider to launch an attack unseen until it was too late. The very idea sparked a desperate, urgent desire to catch up, to surpass, to ensure that America, too, could master this new boundless frontier. Incidents like the Berlin crisis further escalated these already heightened tensions. Each political standoff, each diplomatic skirmish, served to underscore the fragility of peace and the ever-present threat of direct confrontation. In such a volatile climate, both nations gripped by mutual suspicion and a relentless drive for strategic advantage began to see the militarization of space not as a regrettable possibility, but as a necessary pathway to security, or at least to perceived superiority. It was a race not just to explore, but to develop nuclear weapons to perfect missile defense systems and to engineer other technologies that could be deployed within the cosmic expanse. Imagine the feverish pace of laboratories and testing grounds where brilliant minds, often driven by patriotic fervor, but also by fear, worked tirelessly to unlock the secrets of this new domain. The stakes were immeasurable, touching upon the very global dominance that both superpowers so desperately coveted. Military planners, those quiet strategists who sat in dimly lit rooms, pondering every conceivable scenario, were particularly absorbed by a chilling question. How might these nuclear weapons, once unleashed in the seemingly boundless void of space, alter the very calculus of global military strategy? This wasn't merely about hitting targets on Earth. It was about a whole new dimension of warfare, where the laws of conventional conflict might cease to apply. More specifically, their thoughts often circled back to a peculiar and deeply unsettling phenomenon: the electromagnetic pulse, or EMP, that would inevitably follow such a colossal explosion. Imagine it as an invisible ripple, a silent, sudden surge of pure energy capable of sweeping across vast distances, disrupting everything in its path. It was an abstract concept, difficult to grasp fully, yet its potential implications were terrifyingly real. An electromagnetic pulse is essentially a burst of electromagnetic radiation, a sudden outpouring of energy typically generated by a nuclear explosion, but its true power is unleashed particularly in high-altitude or space-based detonations. Think of it not as a shockwave you can feel or a sound you can hear, but as a blinding flash of invisible light radiating outward in all directions. This pulse, this silent storm, possessed the capacity to generate powerful electric and magnetic fields. Now picture those fields vast and unseen as they spread through the very air we breathe and the devices that underpin our modern lives. They are capable of disabling electrical circuits, turning complex machinery into inert husks. They can disrupt communications, severing the invisible threads that connect our world, plunging us into a sudden, unsettling silence. And perhaps most chillingly, they can cause widespread damage to infrastructure, turning the lifelines of civilization, like vast power grids, intricate networks of satellites, and even simple radio systems, into fragile, vulnerable targets. Back in the early 1960s, scientists, with their quiet, persistent observations, already knew that nuclear blasts, regardless of their location, produced EMPs. This was not a complete unknown. However, the true full scale and potential damage of such EMPs, especially those unleashed in the boundless vacuum of space, remained largely a mystery. It was like knowing a fire could burn, but not comprehending its ability to ignite an entire forest from miles away. The theories were there, the mathematical models existed, but the empirical data, the real-world observations of such an event, were absent. There was a desperate need to understand this unseen force, to measure its reach, and to comprehend its true destructive power. It was a dark scientific curiosity, born out of necessity and the grim reality of the nuclear age. And so, Operation Fishbowl emerged as more than just a military exercise. It was a profound, albeit dangerous, scientific endeavor. It was a chance to finally gaze upon these unknown effects more closely, to peel back the veil of uncertainty and confront the true nature of this invisible threat. The very sky, once a canvas for stars and dreams, became a laboratory, a crucible where humanity dared to unleash forces it barely understood, all in the chilling pursuit of knowledge and dominance. Imagine the quiet tension in the control rooms, the hushed voices of scientists and engineers as they prepared to conduct these unprecedented experiments. Each launch was a gamble, a step into the unknown. The sky above, usually a symbol of peace and wonder, was about to become the stage for a spectacular yet terrifying display of human ingenuity and its potential for unintended consequences. The echoes of these detonations would resonate for decades, shaping policies and perceptions in ways no one could have fully foreseen. It was a story woven with threads of ambition, fear, scientific discovery, and the profound weight of human responsibility, all unfolding beneath the silent, watchful gaze of the cosmos. And as we consider this, let us pause for a moment and reflect on the delicate balance that humanity always seeks. On one hand, the relentless drive to explore, to understand, to push the boundaries of what is known. On the other, the profound responsibility that comes with wielding such immense power, particularly when the full scope of its effects remains shrouded in mystery. It is a dance between light and shadow, between progress and peril, played out on the grand stage of the universe. The notion of an EMP, an unseen wave of destructive energy, forces us to contemplate the interconnectedness of our world in a new light. We build vast, intricate networks of wires, signals, and machines, believing them to be robust, resilient. Yet the possibility of an unseen force emanating from far above, capable of unraveling these threads in an instant, highlights a fundamental vulnerability we often overlook. It's a quiet reminder that even our most advanced technological creations are still subject to the whims of forces far grander and more complex than we might sometimes assume. Think of our daily lives, so deeply intertwined with the unseen flow of electricity, the constant hum of communication. From the gentle glow of a bedside lamp to the intricate dance of global financial markets, every aspect relies on these delicate currents. The idea that a single distant flash could disrupt this entire symphony is both a chilling thought and a powerful invitation to consider the true fragility of our engineered world. It prompts us to ask softly if our pursuit of technological mastery has perhaps outpaced our wisdom in safeguarding its foundations. And so, with these thoughts gently stirring within us, we leave this first contemplation, this quiet exploration of the Cold War's reach into the cosmic realm. We have peered into the ambitions, the fears, and the unknown questions that propelled humanity to unleash forces it barely understood, all in the silent, star-dusted arena above. The stage is set, the players are in motion, and the true consequences are yet to unfurl like a scroll slowly unrolling in the vast emptiness of space. Now let us turn our attention to the heart of this cosmic endeavor, Operation Fishbowl. This was not merely a singular event, but a carefully orchestrated series of 5 nuclear tests conducted in the quiet vastness of outer space by the United States. Imagine the meticulous planning, the scientific rigor, and the profound, perhaps unsettling curiosity that drove these experiments. Their aim, as we softly explored, was a fascinating and chilling duality, both military and scientific. It was as if humanity, perched on the edge of a new frontier, sought to answer 2 very different, yet equally pressing questions with a single, colossal bang. On the military side, the objectives were rooted deeply in the anxieties of the Cold War. Planners sought to study the effectiveness of nukes as anti-ballistic missile measures. Picture an incoming enemy missile streaking silently through the atmosphere, a spear aimed at the heart of a nation. Could a nuclear explosion detonated far above somehow intercept or neutralize this threat? It was a question born of desperation and the relentless pursuit of an impregnable defense. They envisioned a shield invisible and powerful, forged not of metal, but of pure destructive energy. The very idea was both a grim necessity and a terrifying proposition. Furthermore, the military strategists harbored a chilling curiosity about how a space-based blast might interfere with electronics communication and military operations on the ground. Imagine our world intricately woven with invisible threads of data and communication radio waves carrying vital messages, delicate electronic circuits powering our daily lives, and the complex dance of military movements guided by unseen signals. Could an explosion far above sever these threads, plunging entire regions into a technologically induced silence, a sudden, debilitating darkness? They sought to understand this potential vulnerability to gauge the extent of the chaos such an event could sow. It was like wanting to know if a single powerful tremor in the fabric of space could unravel the very tapestry of modern life below. Now shift your gaze to the other side of this dual ambition, the scientific yearning. Here the questions were perhaps less about destruction and more about fundamental understanding, though the means remained terrifyingly similar. Scientists wanted to know how a space explosion would impact the Earth's magnetosphere. Imagine our planet cradled within an invisible protective bubble, a grand magnetic shield constantly deflecting harmful solar winds and cosmic rays. This magnetosphere is a delicate living entity pulsating with unseen energy vital for life on Earth. How would an unprecedented infusion of raw human-made power affect this natural guardian? Would it ripple, distort, or perhaps even tear this celestial shroud? And then there was the enigmatic question of what kind of electromagnetic pulse it would generate. We touched upon the EMP earlier, that invisible surge of power. But here, the scientific curiosity delved deeper. What were its precise characteristics when born in the vacuum of space? How would it propagate through the cosmic ether? What unknown physical laws might govern its spread and its interaction with our planet's delicate systems? It was a journey into the uncharted waters of high-altitude physics, driven by a profound need to map the contours of this powerful unseen phenomenon. This delicate dance between military necessity and scientific exploration culminated in Starfish Prime, which was not just a blast, but the first blast of the bunch. Imagine the morning of July 9th, 1962. The vast open expanse of the Pacific Ocean, almost 1,500 kilometers west-southwest of Hawaii, became the silent stage. A Thor rocket, a slender pillar of human ambition and ingenuity, stood poised against the dawn sky. And within its metallic shell, nestled deeply, was a fearsome payload, a 1.4 megaton thermonuclear warhead. To truly grasp the immense power contained within that single device, consider this: it was 500 times more powerful than the one that destroyed Hiroshima. 500 times the force that reshaped a city and altered the course of history, now ready to be unleashed in the heavens. But this was not merely a destructive act. It was also a profound, if terrifying, scientific experiment. Accompanying the colossal warhead were 27 smaller missiles, each a nimble messenger loaded with scientific instruments. These miniature sentinels were fired up alongside the main rocket, their sole purpose to gather data on the blast itself and its subsequent far-reaching effects. Imagine them, tiny eyes and ears rushing towards an inferno, eager to whisper back secrets from the heart of an unprecedented event. They were designed to capture every tremor, every flicker, every ripple of energy from this cosmic unfolding. As the Thor rocket raced upwards, piercing the thinning veil of Earth's atmosphere, it carried its formidable cargo higher and higher, a silent arrow aimed at the stars. And then, at an altitude of 400-kilometer height, roughly equivalent to where the International Space Station now gracefully orbits, the nuke finally exploded. Imagine that moment, a controlled yet utterly unleashed detonation in the pure vacuum of space, far above the concerns and the clamor of the world below. What a sight it must have been. For those on Earth far below, the experience was profoundly alien, yet undeniably spectacular. Ionized particles from the explosion collided with molecules in the Earth's atmosphere, like countless tiny sparks igniting an ethereal canvas. The result was a breathtaking display, widespread auroras visible across the Pacific. These were not the gentle, shimmering northern lights born of solar winds. These were brilliant, human-made curtains of light stretching thousands of miles, painting the night sky with hues unseen before. They were so vast, so profound, that they were even observed as far away as New Zealand, a testament to the immense reach of this man-made cosmic brushstroke. Just below the explosion in the soft, cloudy night sky of Honolulu, a different kind of spectacle unfolded. The sky was not merely lit. It was illuminated for a full 6 minutes. Imagine the astonishment, the sheer disbelief as the familiar darkness of night was pierced by a blinding artificial dawn. It was as though another sun had emerged at 11 p.m., hanging silently above the city, casting long, unmoving shadows where none should have been. This was no fleeting flash, but a sustained, unsettling brilliance, a defiant act against the natural rhythm of day and night, and the effects were not merely visual. Down on the ground, the invisible ripples of the blast began to assert their presence. Radio stations wavered, their signals twisting and distorting, as if caught in an unseen current. A sudden jarring siren was set off, its wail piercing the surreal silence that had descended upon the city, a mechanical cry of alarm. And then, in a chilling testament to the unseen power unleashed above streetlights across Hawaii, were even knocked out, plunging familiar avenues into an unexpected sudden darkness. It was a tangible, unnerving demonstration of how fragile our engineered world could be, how deeply connected it was to the invisible forces that coursed through the very fabric of existence. The quiet hum of civilization was abruptly, if temporarily, silenced by a force unleashed in the void. The theoretical understanding of these phenomena, particularly the electromagnetic pulse, had always been a complex and abstract field of study. Scientists often working in isolated laboratories grappled with equations and models that sought to predict the behavior of nuclear explosions in various environments. They knew in principle that an EMP would be generated. But the true scale, the actual devastating reach of such an invisible storm, was something that could only be truly understood through direct observation. And Starfish Prime provided that grim, unprecedented opportunity. Imagine the countless calculations, the intricate diagrams, the long nights spent debating theoretical outcomes. Yet all of that remained firmly in the realm of speculation until the moment the Thor rocket detonated. It was then that the abstract became terrifyingly real, the theoretical predictions manifesting in tangible, unsettling ways across the Hawaiian Islands. The sight of streetlights flickering and dying, not due to a local power outage, but because of an event hundreds of kilometers above, must have been a profoundly humbling and alarming experience for those who witnessed it, and for the scientists who analyzed the data. This event was more than just a test. It was a profound, accidental revelation. It peeled back a layer of the unknown, exposing a new dimension of vulnerability that humanity had not fully appreciated. The very air, once thought to be merely a medium for sound and breath, revealed itself as a conduit for an unseen powerful force. And the fragile web of human technology, so carefully constructed, proved to be acutely susceptible to this cosmic tremor. It was a stark, silent lesson, taught by a flash in the dark. The historical context surrounding Starfish Prime is crucial, almost like the hidden roots of a mighty tree, feeding its profound impact. The early 1960s were not just any years. They marked one of the most tense periods of the Cold War. Picture the world as a vast chessboard with the US and the Soviet Union locked in a fierce struggle for global dominance. Every move was scrutinized. Every gain for one side felt like a loss for the other. It was a relentless silent battle fought across political, economic, and ideological landscapes. Both superpowers, driven by a deep-seated desire to outmaneuver and outperform their rival, sought to outdo each other in military strength, political influence, and technological prowess. This wasn't merely about national pride. It was about shaping the very future of the world, about defining the prevailing system of governance and thought. Every innovation, every breakthrough became a weapon in this quiet yet intensely charged conflict. And in this grand unfolding drama, the space race became a key battleground. It was a new frontier, a pristine canvas upon which each nation could paint its narrative of superiority. By 1961, the Soviets, through their early successes, truly seemed to have the upper hand. They had successfully sent the first rocket into space in 1957 Sputnik 1, a constant beeping reminder from the heavens. And just 4 years later, Yuri Gagarin became the first human in space, a triumph that resonated deeply across the globe, inspiring awe, and in the West, a profound sense of urgency. Imagine the growing pressure on the US, the quiet anxieties that permeated the halls of power. There was a palpable fear that the Soviets might develop space-based military power before them. This wasn't merely a theoretical concern. It was a strategic nightmare. The ability to deploy weapons from orbit to gain an unchallenged vantage point could fundamentally alter the balance of power, rendering traditional defenses obsolete. With tensions escalating after incidents like the Berlin crisis, where the ideological divide felt almost tangible, both nations, caught in a cycle of suspicion and fear, saw the militarization of space as a way to gain a strategic advantage in the Cold War. It was a grim logic, born of a desperate need to secure oneself in an increasingly volatile world. This belief sparked an intense, almost feverish race to develop nuclear weapons, missile defense systems, and other technology that could be deployed in space. The heavens, once seen as a realm of wonder and pure scientific inquiry, were quickly being transformed into a potential battleground. Military planners, with their quiet analytical minds, were particularly concerned about how these nuclear weapons could be used in space and what effects the detonation of such weapons might have on global military strategy. This wasn't just about the physical explosion, the raw destructive force. It was about the cascading consequences, the unseen ripples that could spread far beyond the immediate point of impact. They grappled with complex scenarios, trying to anticipate every possible outcome of unleashing such power in the cosmic void. More specifically, as we have touched upon, they were profoundly worried about the electromagnetic pulse, or EMP, that would follow such an explosion. Imagine this EMP not just as a burst, but as a silent, powerful scream echoing through the invisible channels of our connected world. An electromagnetic pulse is a sudden, intense burst of electromagnetic radiation produced by a nuclear explosion, especially those occurring at high altitude or as space-based detonations. Think of it as a ripple in a cosmic pond, but this ripple is made of pure energy traveling at the speed of light, capable of reaching across continents in an instant. This pulse, this invisible wave, can generate powerful electric and magnetic fields that are capable of terrifying things. Imagine it washing over our modern infrastructure, disabling electrical circuits, turning power grids into useless networks of wire, silencing the very heart of our technological society. It can disrupt communications, severing the invisible threads that bind us, plunging cities and nations into a sudden, isolating silence. And perhaps most chillingly, it can cause widespread damage to infrastructure like power grids, satellites, and radio systems, leaving behind a trail of darkness and disconnection. Back in the early 1960s, scientists, with their meticulous observations and careful hypotheses, already knew that nuclear blasts produced EMPs. This was not a secret. However, the full scale and potential damage of such EMPs was not well understood. It was like knowing that a match could start a small flame, but not comprehending that it could ignite an entire forest from miles away. The theoretical models existed, but the real-world data, the tangible evidence of such widespread disruption, was still a terrifying unknown. And so, Operation Fishbowl was a chance to study these effects more closely. Launched from Johnston Atoll, a remote speck of land in the vast Pacific, it became the crucible for these unprecedented experiments. Imagine the isolation of that place, the profound sense of being at the very edge of the known world, preparing to unleash forces that could reshape it. Starfish Prime, as we explored, was just the beginning. 3 months after that initial spectacular blast, the US launched the remaining 4 tests in a span of just 2 weeks. It was a furious pace, a concentrated effort to gather as much data as possible, as if racing against an unseen clock. The second test, chillingly named Checkmate, launched on October 20th, 1962. This was a smaller device, a 20-kiloton bomb similar in size to the one that had been dropped on Hiroshima. It detonated at a lower altitude, only 147 kilometers, bringing the effects closer to the Earth's delicate atmospheric layers. This was rapidly followed by bluegill triple prime on the 26th of October, then kingfish on November 1st, and finally tide rope on the 4th of November 1962. Each of these subsequent tests had specific objectives aiming to probe different aspects of nuclear detonations in various atmospheric and orbital altitudes. Bluegill triple prime and tightrope were both smaller explosions detonating at 48 and 23-kilometer altitudes, respectively. Bluegill triple prime was aimed at understanding lower atmospheric effects of such explosions in the mesosphere, delving into how these powerful forces might interact with the delicate mid-layers of our planet's atmosphere. Tightrope, on the other hand, was conducted as an anti-missile test in the stratosphere, probing the possibility of using nuclear blasts as a defensive measure against incoming threats in a layer closer to Earth, but still far above conventional flight paths. It's interesting to note, and perhaps a gentle reminder of how definitions shift, that NASA defined space as starting at an altitude of 80 kilometers. So in the strictest sense, these two lower altitude tests weren't strictly carried out in space as we commonly imagine it today. They were on the very edge, probing the delicate boundary where Earth's breath thins into the vacuum. Kingfish, a more substantial blast at 0.41 megatons, detonated 95 km above sea level. This placed it firmly in the lower reaches of what we consider space, a powerful echo of Starfish Prime's higher, more spectacular debut. But even Kingfish with its formidable power paled in comparison to the explosion of Starfish Prime. The sheer scale of that initial blast, its breathtaking visual effects, and its profound unseen consequences established it as the most significant and unsettling of the entire series. It was Starfish Prime that truly unveiled the terrifying potential of high-altitude nuclear detonations, painting a canvas of light and invisible destruction across the vast Pacific sky. The immediate impact of Starfish Prime struck awe into those who saw it. Imagine the profound silence, the chilling beauty of aurora, stretching thousands of miles, a vast ethereal curtain of light dancing across the cosmic stage. And then, the unnerving sight of a fireball over Hawaii, a momentary artificial sun illuminating the cloudy night sky for minutes. All this unfolding in total silence. Unlike explosions on the ground, when a nuclear detonation happens in space, you can't feel a shock wave, nor can you hear a sound. The vacuum of space simply does not carry these familiar echoes of destruction. There is no towering mushroom cloud, no distinctive double flash that marks an atmospheric explosion. Instead, there's just a bright ball of plasma, a swirling incandescent sphere of superheated gas. This plasma ball changes colors almost like a lava lamp as charged particles from the explosion are pushed down into the atmosphere by Earth's powerful magnetic field. It's a silent, mesmerizing dance of light and energy, ethereal, yet born of unimaginable destructive power. These colorful, almost beautiful auroras gave high-altitude nuclear explosions the chilling nickname of rainbow bombs, a name that in its very contrast hints at the disturbing beauty of something truly terrifying. But the lasting effects of such an explosion are far from sunshine and rainbows. The initial awe gives way to a deeper, more profound understanding of the unseen and far-reaching consequences. Starfish Prime impacted the Earth in two significant ways: two vast invisible wounds inflicted upon our planet and the delicate environment that surrounds it. And it is here, as we begin to contemplate these deeper scars, that we understand the true weight of what was unleashed that silent night. The story continues to unfold, revealing layer after layer of a complex and unsettling truth, much like the slow, silent unraveling of a cosmic secret. Imagine, if you will, the quiet hum of scientific discovery that preceded these dramatic events. In 1958, a seemingly humble U.S. space mission Explorer 1 made a groundbreaking discovery. It unveiled a hidden layer of our cosmic home. The Earth is surrounded by two donut-shaped regions of intense radiation. Today, we call them Van Allen belts, named after the brilliant scientist who first unveiled their existence. These belts are not empty space. They are vibrant, dynamic regions made up of charged particles, mainly protons and electrons, forever trapped by Earth's powerful magnetic field. Think of these belts as an invisible protective shell, a magnificent celestial guardian, constantly deflecting harmful solar radiation and cosmic rays. They act as a cosmic net, gracefully capturing high-energy particles from the sun's solar wind, safeguarding life on our planet from the harsher realities of space. It's a natural shield, a testament to the intricate balance of forces that allow life to flourish here. But the Starfish Prime explosion, in its brute human-made power, unleashed such a quantity of charged particles into Earth's magnetosphere that it fundamentally altered the composition and intensity of the natural Van Allen belts. It was as if a delicate ancient tapestry had been violently torn and then rewoven with crude alien threads. Not only did it disrupt the existing belts, but it even created artificial radiation belts that were stronger and longer than the originals. These unwelcome additions, these phantom shields, persisted for up to a decade. Imagine a scar on the very fabric of space, slowly, gradually fading over 10 long years. This lingering cosmic wound had profound and immediate consequences for humanity's burgeoning ventures into space. These artificial belts began to shorten the lifespans of several satellite systems, turning carefully engineered machines into fragile, doomed travelers. The constant bombardment of excess radiation slowly eroded their delicate components, leading to their premature demise. It was a silent, invisible assault on the very infrastructure of early space exploration. These belts also interfered with telecommunications, causing static and disruption in the invisible pathways of global communication, a tangible reminder of the far-reaching effects of the unseen. Perhaps most tragically, they directly destroyed two early satellites, Ariel 1, Britain's first satellite, a symbol of national pride and scientific ambition, and the first TV broadcasting satellite, Telstar 1, a marvel of communication technology designed to bring the world closer together through moving images. Both innocent bystanders in a cosmic experiment became silent casualties, their brief lives in orbit cut short by the lingering unseen touch of the rainbow bomb. It was a stark, undeniable demonstration of the unintended consequences of human action on a grand cosmic scale. But that's not all Starfish Prime did. Remember the electromagnetic pulses, EMPs, we spoke about earlier? That silent, invisible storm. Scientists knew the blast would emit them, but no one could have guessed just how intense they would be. The true scale of this phenomenon was utterly unprecedented, a revelation that would forever alter the understanding of nuclear warfare and its chilling reach. Nuclear detonations in their fundamental physics emit gamma rays in all directions. Think of these gamma rays as tiny, incredibly energetic bullets spraying outward from the point of explosion. This initial burst is known as a Compton current. When these gamma rays interact with Earth's atmosphere, even the very thin upper atmosphere, they violently ionize air molecules and liberate high-energy electrons. It's like a colossal electrical storm triggered not by nature but by human hands. Since Starfish Prime detonated at an altitude of 400 kilometers, these gamma rays collided with atoms in the upper atmosphere, creating a cascade of free electrons. And here's where the Earth's natural defenses unwittingly amplified the destructive power. These liberated electrons were then accelerated by Earth's magnetic field. Imagine them caught in an invisible, powerful current, swirling and gaining immense speed. This acceleration produced a rapid and intense oscillation of electromagnetic fields at high altitudes. In these thin, rarefied regions of the atmosphere, where there's less resistance, this pulse is able to spread much further than it would in a low-altitude explosion. It's like a whisper that travels across a vast, quiet hall, far more effectively than a shout in a crowded room. The EMP from Starfish Prime spanned thousands of kilometers of vast invisible net cast across the Pacific. It was capable of damaging electrical systems far from the detonation site. Imagine the shock, the bewilderment as tangible real-world effects manifested not just directly beneath the blast, but at distances previously unimaginable. Almost 500 kilometers away in Hawaii, the effects were chillingly apparent. Streetlights went out, plunging familiar neighborhoods into sudden darkness. Telephone lines were disrupted, severing vital connections. And radio communications were affected, turning clear signals into static and silence. This event was a stark, undeniable mirror, showing how vulnerable civilian infrastructure is to such an event. It was a lesson taught not in a classroom, but in the sudden darkness of a Hawaiian night, a silent testament to the interconnectedness of our fragile modern world. Starfish Prime made the world realize just how destructive an EMP can be. It unveiled a new terrifying dimension of warfare, a silent weapon capable of crippling an adversary without ever firing a direct shot. It revealed how vulnerable electrical grids, communications, and satellites would be to a nuclear EMP attack if added to the strategic arsenal. Such a capability would give any military the capacity to cripple enemy infrastructure without direct contact or bloodshed. It was a chilling revelation, a silent blueprint for a new kind of war, and the story of Starfish Prime's unseen reach continued to unfold. The explosion also released an isotope called cadmium-109. This seemingly innocuous substance, a tiny chemical signature, became a silent tracker of the fallout, used to track the fallout and measure resulting contamination. While ground tests normally leave behind a characteristic localized fallout pattern contained to a specific area, the effects of space testing were profoundly, unsettlingly global. Imagine the surprise and then the deep concern when New Zealand rainwater was found to be contaminated with cadmium-109. Far from the Pacific detonation site, on an island nation untouched by the immediate flash, the lingering touch of Starfish Prime was detected in something as simple and vital as rain. A 1966 Nature article specifically attributed this contamination to Starfish Prime, solidifying the global reach of this cosmic experiment. These kinds of reports, quiet scientific observations from around the world, raised significant environmental concerns about the long-term impact of space-based detonations on Earth's atmosphere and environment. It was a realization that our actions in the vastness above could have subtle, yet profound and far-reaching consequences for the very planet we inhabit. The idea that a single detonation far away in space could subtly alter the chemical composition of rain falling on distant shores was a powerful and sobering thought. And imagine this Starfish Prime wasn't even the biggest bomb the US had ever detonated on the edge of space. That grim prize goes to Tick from Operation Hardtack in 1958. At 388 megatons, it was over twice as big as Starfish Prime and detonated at a slightly lower altitude of 76.8 kilometer. Tick, like its later counterpart, turned night into day, a momentary blinding sun. But it also cut many trans-Pacific high-frequency communication circuits, silencing vast swathes of international communication. According to the Nuclear Defense Agency report on Operation Hardtack, Tick literally destroyed the ability of the normally ionized layers of the upper atmosphere to bend radio waves back to the Earth. It was a direct, devastating assault on the very mechanisms that enabled long-distance communication in that era. It showed that these powerful detonations could not only disrupt, but actively obliterate the invisible infrastructure of global connectivity. But the Americans were not alone in this grim exploration. The Soviets were also busy testing high-altitude nuclear explosions, pursuing their own understanding of these terrifying phenomena. They detonated 7 space bombs over Kazakhstan between 1961 and 1962, a series known chillingly as Project K. Their aims and effects were much the same as the U.S. tests to understand the military implications and scientific consequences of such blasts. These Soviet detonations ranged in altitude between 40 and 300 kilometers, covering a spectrum of atmospheric layers. None were quite as big as the American bombs, ranging in size from 1.2 to 300 kilotons, with even their largest being about 5 times smaller than Starfish Prime. Yet their impact was no less significant. On October 22, 1962, a 300-kiloton missile warhead, known as Test 184, detonated at an altitude of 290 kilometers. The EMPs generated from this single explosion were powerful enough to start a fire that burned down the Karaganda power plant and remarkably blew over 1,000 kilometers of shallow buried power cables between Selenograd and Alma. Imagine the chaos, the sudden darkness, the unexpected destruction caused by an unseen force emanating from the distant sky. These were not just theoretical models or abstract scientific data. These were real tangible impacts on critical infrastructure, demonstrating the profound, immediate, and unsettling power of the EMP from space. These learnings, gleaned from both sides of the Iron Curtain, had serious Cold War implications, illuminating a new terrifying dimension of warfare. They highlighted with chilling clarity the urgent need for international agreements to prevent nuclear testing in space. The unintended consequences, the unseen ripples of destruction, were simply too vast, too unpredictable, and too dangerous to ignore. As the echoes of these colossal explosions began to settle, a profound shift began to occur in the collective understanding of the Cold War powers. The unforeseen consequences of Starfish Prime, along with the chilling lessons learned from the Soviet Project K, eventually led both superpowers to reconsider space-based nuclear strategies. It was a gradual dawning, a quiet realization that the very weapon they sought to master held unpredictable, potentially self-defeating power. The sky, once seen as a blank canvas for ultimate dominion, had revealed itself to be a delicate web, easily torn with unforeseen repercussions for all. Imagine the quiet, intense diplomatic discussions that must have followed the careful weighing of unprecedented data, the grim recognition that these cosmic experiments had unveiled a vulnerability far greater than anticipated. The very act of seeking an advantage in space had inadvertently exposed a global fragility, proving that even in the vast emptiness, our actions could ripple back to touch every corner of our shared home. And so, just 1 year later, in 1963, a landmark moment of fragile peace emerged from the shadow of these cosmic blasts. The Limited Nuclear Test Ban Treaty was signed by the US, UK, and USSR. This was more than just a piece of paper. It was a global sigh of relief, a collective agreement to step back from the precipice of environmental and strategic uncertainty. The treaty specifically prohibited nuclear weapon tests in the atmosphere, outer space, and underwater. Its core purpose was clear: to reduce radioactive fallout that could silently contaminate distant lands, and to curb environmental contamination that threatened the delicate balance of our planet. It was a recognition that even invisible fallout could have tangible, long-lasting consequences, silently weaving itself into the very fabric of life. Yet this initial agreement, while crucial, was only a first step. The concept of space as a potential battleground still lingered a haunting whisper in the minds of strategists. More clarity, more robust safeguards were needed to truly ensure the peaceful nature of this new frontier. And so, a few years later, in 1967, the even more comprehensive Outer Space Treaty followed. This profound document went further, solidifying the commitment to keep the cosmos a realm of peace and discovery. It explicitly banned the placement of nuclear weapons or other weapons of mass destruction in outer space. This was a critical safeguard, ensuring that no nation could position a doomsday device above the Earth, ready to unleash destruction from orbit. Imagine the vision behind this, preventing the heavens from becoming a silent arsenal, poised to rain down chaos. The treaty also forbade nuclear explosions in space or on celestial bodies, sealing off the entire cosmic domain from such devastating tests. It was a powerful, forward-looking agreement designed to ensure that space remained a domain for peaceful exploration and not military confrontation. It painted a vision of the cosmos as a shared heritage, a place for universal curiosity, rather than a new arena for human conflict. Now let us bring these lessons into the present and contemplate how our modern world relies heavily on space-based infrastructure. It's an invisible web intricately woven that underpins nearly every aspect of our daily lives, often so seamlessly that we take it for granted. Satellites are no longer mere scientific curiosities. They are the silent architects of our global connectivity. They underpin global navigation, guiding our journeys with unseen precision. They enable communications, allowing voices and data to traverse continents in an instant. The very internet we rely on, the GPS that guides our cars and phones, the weather forecasts that shape our days, all depend on these tireless sentinels orbiting high above. Imagine then the profound, instantaneous chaos that a nuclear explosion in space would spell for us below. It wouldn't just be a localized disruption. It would be a global unraveling. The delicate threads of our interconnected world would snap. Global commerce and trade routes would crash and grind to a halt as ships, planes, and supply chains lose their navigational guidance and communication links. Our electronics and power grids would be fried, bringing critical services to their knees, plunging vast regions into darkness and technological silence. Think of cities humming with electricity, suddenly quiet, inert. The impact would cascade into every corner of our lives. Hospital equipment would stop working, jeopardizing countless lives that depend on continuous, precise technological support. Millions of tons of food would go to waste without proper preservation as refrigeration systems fail and supply lines collapse, and the intricate global dance of financial markets would collapse, triggering an economic crisis of unimaginable scale. The very foundations of our organized society, built on the assumption of constant connectivity and reliable infrastructure, would crumble. The effects of a nuclear EMP would be far more devastating today than they were in the 1960s. This is because our vital global systems and everyday lives rely much more on electronics than they did back then. In the 60s, a streetlight going out was a nuisance. Today, it's a symptom of a far deeper, more catastrophic systemic failure. We have woven ourselves into a delicate technological web, and the forces unleashed by a space-based EMP could tear it apart with chilling efficiency. We've established that various international treaties are in place today to ban further nuclear space explosions. These are the pillars of our collective hope for a peaceful cosmos. But this leads us to a crucial, unsettling question. Could such catastrophic events caused by an EMP still occur in some form today? The shadows of the past sometimes lengthen into the present, hinting at vulnerabilities that remain, perhaps even grow despite our best intentions. Let's gently consider a historical echo, a natural phenomenon that, while not human-made, offers a glimpse into the kind of cosmic disruption we fear. In 1859, the world experienced the largest ever recorded geomagnetic storm, the Carrington event. Imagine a colossal burp from our sun, a powerful coronal mass ejection CME that slammed directly into Earth's magnetic field. This wasn't a human weapon, but a raw, untamed force of nature. The effects were startling, almost whimsical, if not for their underlying power. Northern lights were reported as far south as Cuba and Honolulu, painting the tropical skies with ethereal dancing colors. They were so bright people in the north of the U.S. could read newspapers just by the light of the aurora. Imagine the awe, the confusion of waking to an artificial dawn illuminated by the very sky itself. But beneath this beauty, there was disruption. It threw sparks from telegraph equipment across the U.S., some strong enough to set fires. This was a world far less reliant on electronics, yet even then, the effects were profoundly unsettling. If a CME of similar magnitude were to occur in our direction today, it could hit us with very similar effects, like Starfish Prime. Our modern hyper-connected world, with its vast, intricate electronic nervous system, would be exquisitely vulnerable. The potential for widespread catastrophic disruption would be immense. Fortunately, the chances of that happening are very slim. These truly powerful CMEs are rare, and the alignment needed for a direct, devastating hit is even rarer. We can breathe a soft sigh of relief on that front, knowing that nature's most violent temper tantrums in this particular form are infrequent. However, the more immediate and perhaps more unsettling risk is a geopolitical one. This brings us back to the complex human-driven dramas that continue to unfold beneath the watchful gaze of the stars. Earlier this year, Russia made headlines for vetoing a UN resolution against putting nuclear weapons in space. This single act, a quiet hand raised in opposition within the hallowed halls of international diplomacy, sent a ripple of concern across the globe. Several news outlets have since speculated that Russia is planning on placing a nuclear warhead in low Earth orbit. While mere speculation, it fuels a deeper anxiety. According to John Plum, an Assistant Defense Secretary for U.S. Space Policy, Russia is actively developing a concerning anti-satellite capability. He describes it as a new satellite carrying a nuclear device that Russia is developing. Imagine the implications: a silent orbiting threat capable of disabling the very eyes and ears of our global society. This capability, if realized, could pose a threat to all satellites operated by countries and companies around the globe. It threatens not just military assets, but the vast, intricate network that supports our daily lives, vital communications, scientific, meteorological, agricultural, commercial, and national security services we all depend on. It would be a silent, indiscriminate sword hanging over the invisible web of our modern world. This development, if true, is in direct violation of the 1967 Outer Space Treaty, that beacon of peaceful exploration we discussed earlier. And here lies a profound vulnerability. Though still in effect, this vital treaty sadly doesn't come with any formal enforcement mechanisms. It relies on good faith, on collective adherence, on the unspoken understanding that its principles are too important to violate. But what happens when that faith is broken, when the unspoken understanding is ignored? These international agreements exist to prevent space from becoming a battleground for nuclear weapons. They are the delicate threads of our collective future, carefully woven to keep the cosmos a realm of peace. They must be respected to ensure all of our safety and well-being. As space becomes increasingly important for modern life, as our reliance on its silent sentinels grows deeper, the lessons of the past are more relevant than ever. Starfish Prime showed us the devastating reality of weaponizing space, the invisible wounds it could inflict, the far-reaching consequences that echo through time and space. The electromagnetic pulses crippled infrastructure, unleashing waves of radiation that lingered in our atmosphere for years, silently eroding the integrity of our cosmic environment. It resulted in destroying satellites and contaminating the space around our planet. This experiment was not just a scientific endeavor. It was a profound, accidental turning point. From its harsh lessons emerged one of the most important lessons of the nuclear and space age. Space could be weaponized in ways that affect not just individual nations, but all of humanity. It was a realization that transcends borders, a chilling whisper about shared vulnerability. This is precisely why international treaties now ban the use of nuclear weapons in space. These agreements are not just legal documents. They are promises to future generations, silent pledges that space will remain a place for discovery and peace, not for conflict and destruction. They are our collective commitment to preserve the cosmos as a realm of wonder, a canvas for shared human achievement, rather than a stage for destructive ambition. This is why responsible, peaceful space exploration is so important. It is our way of ensuring that we can continue to unravel the mysteries of the universe and make discoveries that inspire and unite humanity, doing so without the lingering shadow of total annihilation. It's a call to elevate our gaze, not just to the stars, but to our own shared humanity, to recognize that the boundless opportunities of space demand a boundless commitment to peace. The path forward, though sometimes uncertain, is illuminated by the quiet wisdom gleaned from past mistakes. We have glimpsed the dark mirror of potential destruction, and now we have the choice to turn towards a future where the cosmos remains a source of shared wonder, a testament to what humanity can achieve when it chooses collaboration over confrontation. Let the quiet hum of distant galaxies remind us of the vastness that awaits and the profound responsibility that comes with reaching for it. And as these thoughts settle gently in our minds, let us consider another story, a small ripple in the larger ocean of space exploration, one that hints at the complexities of human nature, even amidst the grandest pursuits. On the 4th of March, 2022, a mysterious rocket booster, an unexpected celestial visitor, crashed into the surface of the moon. This event, while seemingly minor in the grand scheme of cosmic events, was watched with keen interest by the scientific community. They had been tracking the booster since 2015, as it silently orbited our planet, a piece of human-made space junk. When it finally crashed, it formed a strange double crater that defied precedent or obvious explanation. It was a curious anomaly, a puzzle piece that didn't quite fit the expected picture. However, other watchers, perhaps with a more philosophical bent, were more curious about its origin. Who had launched it? Intriguingly, no nation claimed to have done so. It simply appeared, drifted, and then impacted, leaving behind a crater and a lingering question mark in the lunar dust. My mind, when I first heard about this, was immediately caught up in the idea of secret government programs or shady corporations launching pirate satellites for a quick profit. It was a thrilling, almost cinematic thought. But as I delved into it, the origins of this mystery rocket actually opened my eyes to an unexpected issue, one that was deeply troubling. It speaks of an era fast in coming, where rather than space being a place of peaceful exploration, it might be rife with danger and conflict. Hopefully, this is something that can be avoided. But the first step is to understand what is happening up there. I'm Alex McCone, and you're watching Astrum. Join me today as we learn the likely origins of this rocket and the unsettling implications its existence casts on space exploration in general. This silent lunar impact, born of a mystery, serves as a gentle reminder that even the vastness of space cannot escape the complexities and challenges of human endeavor. It beckons us to consider how our rules, our agreements, and our very nature will shape the future of this ultimate frontier. To begin with, figuring out the origins of the rocket booster, known prosaically as WJ13A, is actually one of the simpler aspects of this cosmic mystery. And no, despite the intriguing whispers of secret agendas, it's likely not the jettison from a secret government program. While admittedly, I do not possess insider knowledge about the classified space programs of all the nations around the world, for indeed such knowledge is held tightly shrouded in layers of secrecy, it turns out that secret space launches are surprisingly difficult to achieve. This very difficulty, this inherent transparency of the cosmos, makes the explanation of a clandestine launch rather unlikely. Consider for a moment the historical backdrop. For the last 70 years, ever since the startling invention of the intercontinental ballistic missile, countries across our small blue planet have become profoundly invested in knowing when other countries are launching rockets. Imagine the profound existential fear that gripped the world during the Cold War. The terrifying possibility that America and Russia might at any moment unleash their nuclear arsenals upon each other. In such a tense, delicate balance, it was quite literally a matter of survival for each to know what the other nation was doing. This imperative, this desperate need for vigilance, drove an incredible expansion of surveillance capabilities. They did this primarily with radar, vast unseen webs of detection, reaching out into the sky, constantly scanning for any anomaly. But they also relied on intricate spy networks, a human element of intelligence gathering, whispering secrets from behind closed borders. When Russia, in its grand pioneering move, launched Sputnik 1 in 1957, that iconic beeping sphere, American intelligence already possessed knowledge of its imminent launch. Even if they chose for strategic reasons not to immediately pass this information on to the American people, the knowledge was there, a quiet, confirming whisper in the ears of those who watched. But since those early days, the world of surveillance has evolved, transformed by relentless innovation. Radar systems and satellites have become so good, they are able to spot launches within minutes. Imagine the precision, the sheer technological mastery required to detect a fiery ascent from Earth's surface almost instantaneously. It is quite simply essentially impossible now to send a rocket up without someone noticing. Rockets, after all, are quite difficult to hide. They are immense pillars of fire and smoke blazing trails across the sky, announcing their presence with undeniable force. And even if by some extraordinary, almost miraculous chance, you did manage to launch it undetected, the vastness of space is incredibly open. It is a cosmic stage bathed in starlight, where even the tiniest speck of light can be observed if one looks closely enough. Even if governments with their powerful but focused instruments somehow missed it, there exists a vast, dedicated community of amateur astronomers across the globe. These are passionate individuals, their telescopes pointed skyward as a hobby, their eyes scanning the celestial expanse with a fervent, quiet dedication. It wouldn't take very long before someone somewhere spotted it, a new point of light or a subtle streak against the familiar constellations. Perhaps then you'd have more success disguising your secret spacecraft as something it wasn't. Imagine if you sent it up disguised as an innocent satellite, its true purpose veiled beneath a benign exterior. Or had it fall off a rocket as if it was simple space junk, allowing it to drift through space in plain sight, yet utterly hidden in its true nature. If our mystery rocket, the elusive AVU-09-93A, was something like this, a wolf in sheep's clothing, that might make more sense fitting into the subtle deceptions of the space age. However, we likely know its true origin, not through whispers or cloaked maneuvers, but thanks to the elegant, undeniable language of a little bit of mathematics. Independent astronomers, those quiet watchers of the night, had been tracking the path of the mystery rocket as far back as 2015. They were not bound by national loyalties or classified directives. Their pursuit was pure curiosity. And by meticulously plotting its course, mapping its intricate dance around our planet and the moon, they were able to perform a remarkable feat. They could calculate the reverse of its trajectory. Imagine unwinding a celestial clock, turning its gears backward to see where its hands once pointed. By doing so, they could work out precisely which nations it had passed over at various points in its past. This rigorous mathematical detective work began to narrow down the possibilities, slowly revealing the likely source of this lunar impactor. While initially, this intricate orbital analysis led some to believe that it was a stage of a SpaceX rocket, a product of modern private space enterprise. This theory was later quietly yet decisively supplanted by a much more probable explanation that it had belonged to the Chinese Chang'e 5T1 mission. The evidence began to align with a precision that mathematics often affords. The mystery rocket's calculated orbit passed directly over China on the same day as the Chang'e 5T1 launch, a striking temporal coincidence. Furthermore, its trajectory, meticulously mapped by independent eyes, matched its course exceptionally well with the known path of the Chinese mission. It was as if two distinct lines drawn by different hands on separate maps suddenly converged to form a single undeniable path. And there was additional evidence, a subtle yet compelling corroboration. Students at the University of Arizona's Space Domain Awareness Lab, equipped with their own specialized tools, used a Raptor's telescope to take a spectroscopic survey of the mystery rocket. Imagine them peering through the powerful lens, not just to see its form, but to analyze the very light reflecting off its surface. This process essentially, by evaluating the type of paint used on it from the light reflecting off it, allowed them to compare its unique spectral signature to existing records of rocket materials. The results were quietly definitive. The spectral signature of the mystery object was a closer match to China's rocket style than to SpaceX's. This subtle chemical fingerprint, revealed by the very light it reflected, spoke volumes. These cooperating pieces of evidence, each independent, yet pointing to the same conclusion, led seasoned astronomer Jonathan McDowell to claim a 90% certainty that the mystery rocket had belonged to China. It was a testament to the power of open scientific inquiry, piecing together a cosmic puzzle with threads of observation and deduction. But the story did not end there, for the human element, with its complexities and political nuances, quickly entered the stage. When approached by journalists and presented with this compelling evidence, China denied it. Foreign Ministry spokesman Wang Wenbin delivered a measured official response. According to China's monitoring, the upper stage of the Chang'e 5 mission, rocket had fallen through the Earth's atmosphere in a safe manner and burned up completely. China's aerospace endeavors are always in keeping with international law. Imagine the weight of those words spoken with the calm authority of official denial. Some astronomers, viewing the situation through a lens of scientific understanding and diplomatic grace, believe that China might have been innocently mistaken here. Perhaps their tracking data, for various reasons, simply didn't account for every stray piece of hardware. But it is also possible, as the quiet observer must consider, that China was not telling the truth, choosing diplomacy over direct acknowledgement. If the evidence was so strongly against them, with independent astronomical analysis pointing so clearly to their origin, why deny it? It's perhaps that last line of Wang Wenbin's statement that offers the vital clue. China's aerospace endeavors are always in keeping with international law. Here lies the crux of the issue. China does not want to be seen as in breach of international law. The implication of accidentally losing track of a rocket stage, especially one that impacts a celestial body, could be seen as a violation of the very principles designed to ensure the responsible use of space. And this is where I start to get annoyed, not necessarily with China alone, but with something which is a worldwide problem. It's a quiet frustration that bubbles up when contemplating the vast, complex, and often overlooked realm of international space law. You might not be aware of it, but it does actually exist, a fragile framework designed to govern our species' burgeoning ventures into the cosmos. Although, if we are to be truly honest, it is a little patchy, a patchwork quilt woven from various treaties and agreements with notable gaps and ambiguities. This body of law is made up of a number of treaties that various countries have signed and ratified over the years. Each treaty represents a collective human effort to bring order and responsibility to the boundless frontier of space. Consider, for example, the Rescue Agreement, a humanitarian accord highlighting nations' responsibilities to help astronauts in distress if they are able. It's a beautiful concept, a recognition that, in the vast, unforgiving vacuum, humanity must stand together, transcending earthly divisions. Or think of the foundational Outer Space Treaty of 1963, a cornerstone of space governance. This treaty enshrines in international law the right of all nations to explore space, affirming a universal freedom to venture into the cosmos. It makes states responsible for all space-related activities of their citizens, a crucial principle holding nations accountable for the actions of their private companies and individuals. And it emphatically maintains that space objects like the moon should only be used for peaceful purposes. This is the treaty that forbids any nation from placing nuclear weapons in space, a critical barrier against the ultimate weaponization of the heavens. It is probably why there are no orbiting satellites with nuclear weapon platforms up there today, silently waiting to rain down destruction on the planet. Furthermore, this treaty makes states liable for damages that they cause in space, and crucially requires them to avoid harmful contamination of celestial objects. And it is this last article that China was likely trying not to run afoul of. While there was likely little tangible harm done by the mystery rocket crashing into the moon is, after all, a vast ancient body accustomed to impacts. It's certainly not a good look to accidentally lose track of your rocket stages and have them crash into things later. Imagine the potential implications if any bacteria were on the rocket, even microscopic hitchhikers, that could cause contamination, irrevocably altering the pristine lunar environment. Even worse, if the rocket part had crashed into a satellite, or if there one day ends up being lunar bases on the moon and the rocket part had hit one of those, then it would have meant China had demonstrably broken international law with tangible, undeniable consequences. The quiet, unspoken rules of space, though sometimes vague, carry the weight of global expectation and potential liability. But why do I suggest that this seemingly minor incident of a lost rocket stage will lead to an era of conflict after all? While it's disappointing, it's certainly not that surprising that a nation would try to hide things to get ahead or to avoid looking bad. And my concern takes issue with more than just the fact that there's an increasing amount of space debris circling in space. Though this is indeed becoming an increasing problem, a growing cloud of silent, dangerous fragments. No, the true cause for alarm, the deeper tremor in the cosmic silence, is the unsettling fact that space law is so unregulated that a rocket's origin was a mystery in the first place. This incident, however small, reveals a fundamental flaw. International law is currently insufficient to ensure the peaceful exploration of space in the years to come. What exists is noble in its intent, a testament to human cooperation, but it is rife with holes and ambiguities. It is like a beautiful, intricate net, but with too many gaps to truly catch all the complexities of human ambition and technological advancement. Let's take, for example, the Outer Space Treaty itself, one of the foundational treaties for the peaceful use of space, signed by 117 countries around the world, including the US, China, Russia, and essentially anyone else with a space program. It states unequivocally that outer space is not subject to national appropriation by claim of sovereignty, by means of use or occupation, or by any other means. This sounds clear, a powerful declaration against territorial claims in the cosmos. But this grand principle is in subtle and often unspoken ways actually being somewhat ignored. How does this idea, this lofty declaration, square with the desires of an increasing number of nations to set up bases and mine places like the moon? If you set up a permanent base on a planet or a moon, that certainly sounds like you're trying to stake a claim to at least part of it, which sounds a lot like claiming sovereignty. And surely claiming resources from a celestial body appears to me to be a form of appropriation. The very act of extracting resources, whether minerals or water ice, inherently implies a degree of ownership or control. The U.S. Artemis Accords, signed by 23 countries, now represent a modern attempt to navigate this legal ambiguity. These accords attempt to get around this by having signatories legally state that they're not appropriating any of the resources they extract from the moon. It's a clever legal maneuver, a linguistic tightrope walk, to reconcile the pursuit of resources with the spirit of the Outer Space Treaty. But other nations viewing this from a different perspective claim that this is nonsense. They perceive the American interpretation as just a new version of the enclosure movement of Britain in the 18th century, where powerful entities simply claimed land as their own, regardless of existing norms. Depending on which legal interpretation is ultimately carried out, there is a distinct risk that any nation that attempts to claim resources from the moon might be in breach of international law. This legal gray area creates an inherent tension, a quiet uncertainty that underlies the grand ambitions of lunar exploration. But clearly this ambiguity, this risk, is not slowing anyone down. The allure of lunar resources, the strategic advantages of a permanent presence, are powerful motivators that seem to override the subtle whispers of legal uncertainty. Furthermore, let us consider another crucial article of the Outer Space Treaty. Its declaration about space being a place for peaceful purposes. It clearly states no nuclear weapons or weapons of mass destruction are allowed in space. This is a powerful, reassuring clause, a strong barrier against the ultimate weaponization of the cosmos. However, and here lies a significant loophole, this applies only to weapons of mass destruction. This leaves a lot of wiggle room, a vast unexplored territory for the development and deployment of weapons of middling destruction or lower. And such ideas, far from remaining in the realm of science fiction, are being actively explored and debated right now. Imagine the subtle linguistic dance, the legalistic interpretations that could be applied to this clause. What precisely constitutes a weapon of mass destruction? Does it refer only to nuclear, chemical, or biological weapons? Or can a conventional weapon, if deployed in space with devastating effect, also be considered a weapon of mass destruction? These are not idle philosophical questions. They are at the heart of the debate about the future of space warfare. In 2003, a full 40 years after the Outer Space Treaty was signed, the U.S. Air Force proposed an idea that perfectly illustrates this gray area. They envisioned placing 20-foot-long tungsten rods, nicknamed rods from God, into orbital launches. These immense rods, essentially solid projectiles, could be fired from space. Imagine them silently falling from orbit, reaching incredible speeds. These falling rods would drop at speeds reaching Mach 10, a terrifying velocity. Upon impact, they would hit with the force of a small tactical nuke, but without the radiation. This was the key: conventional destruction, but no lingering radioactive contamination, circumventing the treaty's primary prohibition. Furthermore, such a weapon would launch far less detectably than a missile arriving in half the time, and would be almost impossible to defend against. It was a terrifying concept, an elegant and chilling reimagining of orbital bombardment. Fortunately, rather than these rods, it was the idea that was dropped as it was deemed too expensive. But crucially, the reason it was shelved was not because it encroached on international law. It was a matter of cost-effectiveness, not legality. This clearly indicates that the current legal framework has significant gaps when it comes to regulating conventional weapons in space, with civilization's increasing reliance on satellites for business communication, banking, navigation, and a host of other applications. Weapons in space are becoming increasingly common. Satellites, those silent workhorses of our modern world, are increasingly becoming a point of vulnerability in a nation's security. Imagine the invisible threads of our global society, each a single point of failure that could be targeted from above. Various nations are now actively developing anti-satellite missiles, ASAT, or defenses against ASAT missiles, not just to threaten others' interests, but to defend their own. This is a complex issue, one that carries unexpected dangers. Space conflict of this kind is not as intuitive as you might think. It's not simply about one satellite destroying another. When Russia tested one such ASAT missile on a test satellite of its own, it sent thousands of pieces of debris into orbit around the planet. These tiny fragments, born of an act of destruction, became silent, dangerous projectiles themselves. Some of these pieces could remain in space for years, silently circling a growing threat to all other orbiting objects. And here's the terrifying part. If they collide with other debris or satellites, those in turn could shatter, creating a cascade effect collectively known as the Kessler syndrome. Imagine a chain reaction where ever-increasing fragments of debris multiply, rendering entire orbital pathways unusable for generations, turning space into an impenetrable, dangerous junkyard. If such conflict became widespread, it could be an end to satellites in space for everyone. It would be a self-inflicted wound on a cosmic scale, destroying the very infrastructure that underpins our modern lives. Interestingly, Russia and China have pushed for a treaty known as PAROS that bans all weapons in space of any kind. This sounds like a sensible, peace-oriented approach, but this proposal is being stonewalled by the U.S., who favor the approach laid out by U.S. President Theodore Roosevelt: speak softly and carry a big stick. The argument here is that perhaps some force in space might actually be necessary for defense, adding to the complexity of the situation. To say that there is a lack of trust between the big superpowers at the moment might be a bit of an understatement, complicating any efforts towards comprehensive disarmament in space. Beyond that, in January 2018, a U.S. company called Swarm was denied permission by the U.S. Federal Communications Commission (FCC) to launch 4 satellites. Despite the denial, Swarm went to India and launched them anyway without government approval. There were legal ramifications for this. The FCC later fined Swarm $900,000 for their actions. But this sets a concerning precedent. As space becomes more and more available for companies with large wallets and few scruples, it may one day become profitable to participate in illegal space ventures. This raises the unsettling question of whether some degree of policing, with some degree of force to back it up, might become necessary to protect the interests of legitimate or scientific spacefarers. Sadly, as has been noted by many analysts, there is a perceived preference from countries on all sides towards rules that promote freedom for their own actions while curtailing the activities and aspirations of others. This fundamental human inclination, this self-serving perspective, complicates the crafting of truly equitable and comprehensive space laws, and yet space needs greater global regulation. If the nations of the world can't agree on some kind of framework for ongoing exploration, there is a distinct risk that space exploration becomes a Wild West rife with conflict, where the more noble aim of scientific advancement is left by the wayside. This would be a profound waste, a squandering of humanity's greatest potential. With a little extra work, international law could become robust enough to prevent this, to ensure that the cosmos remains a place of shared wonder, rather than a new arena for earthly disputes. What has been agreed so far shows promise a fragile hope for the future. One treaty, known as the Moon Treaty, attempts to lay out a more comprehensive framework. It clearly states that the environment of the Moon is the common heritage of mankind, to be used only for peaceful purposes, and only to be exploited at the careful agreement according to an international regulatory regime. This sounds like a beautiful cooperative vision for the future. However, a critical flaw exists. Not many nations have signed up to this treaty. Crucially, none of the nations that have their own significant launch capabilities, such as the US, Russia, or China, are signatories. This unfortunate reality leaves this treaty largely ineffectual, a noble ideal, without the power to truly shape the future. There so far has not been any agreement on what this regime would look like, nor what the common heritage of mankind actually means in practical terms. If space is truly going to be a safe place for future generations, this needs to change. More discussion needs to happen on these topics to rein in future illegal activity or escalating space-based arms races. Groups that send rockets into space need to keep track of them, ensuring accountability for every piece of hardware launched into the void. Ultimately, the nations of the so-called civilized world need to come to more agreement on these issues to forge a stronger, more cohesive framework for our shared cosmic future. At the end of the day, we don't want to live in a world where we have mystery rockets crashing into the moon, leaving behind unanswered questions and unsettling implications. We want to live in a world where space is appreciated for its alien beauty, where its dangers and mechanisms are purely natural and understood, and the moons and planets out there can be explored peacefully and fairly, rather than fought over and ultimately destroyed. Maybe as a people, we need to grow up, not just technologically, but civilly too, to match our grand ambitions in space with an equally grand commitment to peace and cooperation on Earth. The cosmos awaits a silent canvas, ready for the brushstrokes of our collective future. What colors will we choose to paint it with? The answer lies within us, in our willingness to learn to adapt and to collaborate under the watchful gaze of the endless stars. For many, the Apollo missions represent the golden era of space travel. It was a decade etched in headlines, a continuous stream of incredible feats that captured the imagination of the world. Each lunar landing, each splashdown earned NASA and their astronauts respect and reverence across the world. They were heroes soaring through the heavens, embodying the very best of human ambition and ingenuity. But just 1 year after completing its mission, Apollo 15 made different kinds of headlines, not of triumph, but of scandal. It was an incident that rocked NASA to its core. Accusations of smuggling, profiteering, and a blatant lack of good judgment landed the proud space agency in a congressional hearing. Imagine the quiet halls of power, usually reserved for policy debates, suddenly consumed by questions of ethics and personal gain. This incident, a stark contrast to the heroic narratives that usually surrounded spaceflight, reduced a mission with a valiant scientific purpose to a backroom operation that stained NASA's reputation at the height of the space race. All this for something seemingly so trivial, 850 g of paper. A small weight, yet it carried an immense burden of ethical compromise. On November 14, 1969, a German man named Horst Eiermann embarked on a journey that would, in an unexpected twist, intersect with the grand narratives of space exploration. He left his Florida home and jumped on a bus to the Kennedy Space Center to watch the Apollo 12 launch. The air must have been thick with anticipation, the roar of the mighty Saturn V, a promise of cosmic adventure. As luck would have it, another German man was on the same bus. Hermann Seeger was a stamp collector and dealer, and remarkably, he turned out to be from the same region in Germany as Eiermann. They shared a common passion, a love for space travel, and became fast friends, perhaps finding camaraderie in the shared wonder of the unfolding space age. Back then, collecting stamps was a popular hobby, a quiet passion shared by enthusiasts across the globe. And in a charming intersection of postal history and cosmic ambition, NASA started printing specially designed covers for each Apollo mission, which were stamped on launch day. These flown covers, as they were known, became highly sought-after souvenirs. They became such a huge part of the Kennedy Space Center's launch days that machines would start rolling from as early as 1:00 a.m. to keep up with demand. Imagine the quiet whirring of the presses in the pre-dawn hours, creating these small pieces of history. These covers made great gifts for astronauts' friends and family, a tangible connection to their incredible journeys, and for NASA employees, a token of their participation in a grand endeavor. Some astronauts, fueled by a desire to make these gifts even more special, took this a step further, transporting postal covers up into space in the command module to then gift their loved ones. It was a small personal touch intended to create a unique memento. Eiermann, as a NASA contractor, knew a lot of people who worked at the Kennedy Space Center, including a number of astronauts. He was well connected, moving within the circles of those who touched the stars. On more than one occasion, driven by a quiet, persistent ambition, he tried to persuade Apollo astronauts to smuggle aboard various stamps and postal covers in exchange for money. So far, he had been unsuccessful. The astronauts, it seemed, had maintained their ethical boundaries. Then one evening in May 1971, while having dinner with the Apollo 15 crew, David Scott Alfred Worden and James Irwin Eiermann tabled a tempting offer. It was a proposition that would subtly yet irrevocably alter the course of their careers and stain a glorious mission. He asked them to carry 100 special stamp covers for Seeger and 300 for themselves. Seeger's covers would eventually be sold off as exclusive collector's items, their value inflated by their journey to the moon. And for their participation in this quiet, clandestine operation, the astronauts would each get a very generous $7,000 for their troubles, which in today's money would equate to about $52 or $300. A significant sum, enough to make even the most dedicated astronaut pause and consider. Initially, the crew were hesitant, their consciences stirring within them. They knew the rules. NASA's standards of conduct explicitly forbade astronauts from using their position to make money for themselves or anyone else. It was a clear line designed to maintain the integrity of the space program and the purity of their scientific mission. But Eiermann, with a smooth confidence, reassured them. He claimed many other Apollo crew members had done the same in the past, implying that this was a common, if unspoken, practice. There was another subtle pressure point Eiermann could exploit. NASA had also recently restructured their employee benefits, meaning astronauts no longer received life insurance. Space is a hostile environment, unforgiving and dangerous no matter how many security measures you put in place. And being an astronaut pushing the boundaries of human endurance is decidedly not a risk-free occupation. Eiermann, with a quiet cunning, played on this vulnerability, convincing them that the money could be put aside to care for their families, should the unthinkable happen on the mission. It was an appeal to their deepest fears, a promise of security cloaked in an unethical proposition. It was and still is fairly normal for astronauts themselves to take personal souvenirs on missions. These are often small sentimental items, tangible links to their lives on Earth carried into the void. Of course, all these personal items needed pre-approval from NASA, before they could fly a meticulous process to ensure the articles were safe for space and compliant with weight restrictions. This was a standard procedure, a careful balancing act of personal mementos and mission integrity. Recall the iconic examples Alan Shepard brought up: a few golf balls and a modified golf club head, famously playing golf on the moon, a whimsical moment immortalized in history. Buzz Aldrin carried on board a communion wafer and a vial of wine, bringing a spiritual dimension to his lunar walk. And indeed, several astronauts carried postal covers on their missions for friends and family back home. These were all approved by NASA prior to launch day, fitting within the established guidelines for personal items. In light of this established practice, accepting Eiermann's proposal may not sound like such a big deal at first glance. It was, after all, just paper. However, just a few months prior, the Apollo 14 crew had taken some silver medallions aboard the spacecraft without NASA's knowledge. This was a similar but perhaps less egregious ethical breach, a deal brokered directly between the astronauts and the production company, the Franklin Mint. After the mission, Franklin Mint melted some down, mixed them with other metals, and mass-produced commemorative medallions. They brazenly used the story that these medallions had been to space in their marketing in an attempt to profiteer. Because the Apollo 14 crew hadn't taken any money for their role in facilitating this, they didn't get into any explicit trouble. The scandal, while noted, didn't become the moral stain on NASA's reputation. It could have been, but it was a clear warning. Remember, all this was happening against the backdrop of the Cold War. Public interest in the space race was at its peak, and astronauts held celebrity status, their images carefully cultivated as symbols of American exceptionalism. Everything that could reflect poorly on American success and NASA's integrity was simply not acceptable in the intense glare of public scrutiny. In light of these previous events, NASA's Director of Flight Crew Operations, Deke Slayton, a man deeply committed to the integrity of the astronaut corps, had expressly warned the Apollo 15 crew against taking anything into space that could make money either for themselves or others. His instructions were clear, unambiguous. They simply couldn't afford more bad press after what happened with the Apollo 14 medallion scandal. The reputation of NASA, the very fabric of public trust, was at stake. With this stern warning in mind, it might surprise you to hear that the Apollo 15 crew eventually accepted Eiermann's deal. Their hesitation had been overcome, their initial reservations set aside, but they did so only on a crucial condition: that absolutely no sales were made until they retired from NASA. It was a desperate attempt to maintain a semblance of ethical conduct, a promise to defer the financial gain until they were no longer representing the agency. A fragile line drawn in the sand based on trust and a delayed gratification. Independently of the agreement with the Germans, it's important to mention another interested party who came to the crew with a similar request. Retired film director and stamp collector F. Herrick Herrick approached Worden. He asked Worden to take 144 covers into space on his behalf. He too promised that they'd be set aside for some years and then sold once all the astronauts had retired from NASA. But unlike Eiermann, he didn't offer Worden any money to transport them. Worden, perhaps trusting the man's reputation, or simply viewing it as a favor for an acquaintance, agreed to go with it. He couldn't have known at the time, but that seemingly innocuous decision set events in motion that would drastically change the course of his life forever. The intricate dance of preparing for a space mission involved countless meticulous steps. On launch day, the Kennedy Space Center post office opened at 1 a.m. EDT, which wasn't unusual on an Apollo launch morning. The demand for those stamped covers was immense. A key member of the crew support team, Collins, brought with him several hundred of the stamped covers to be run through the cancellation machine before taking them to the astronaut quarters. These were the legitimate covers destined to become prized mementos. Members of the flight crew support team then meticulously vacuum sealed the 243 approved covers in Teflon-coated fiberglass to fireproof them for space. This was standard procedure, ensuring safety and integrity. This approved batch included the 144 Herrick covers, which had gone through the proper channels and were approved by NASA ahead of the launch. Everything seemed to be proceeding as planned, a meticulous choreography of preparation. However, a subtle yet ultimately critical error occurred. As team lead James Smotherman was carrying out final checks on the astronauts' personal preference kits, those small bags of approved personal items each astronaut carried, he came across the 400 undeclared Seeger covers. They were there brazenly, right there with the legitimate items, a piece of contraband waiting to be smuggled into orbit. In that moment, through a simple twist of fate and a momentary lapse, he mistook them for the approved covers traveling aboard Apollo 15 and thought nothing of them. In his own words, a quiet confession of human error, he goofed. And just like that, with an almost unbelievable simplicity, the bootlegged Seeger covers slid into David Scott's spacesuit pocket, destined for a journey beyond Earth, bound for the moon. A small, seemingly insignificant detail, yet it carried the weight of future controversy and scandal, unknowingly contaminating a mission of grand scientific purpose. The die was cast, the stage was set for a betrayal of trust that would ripple back to Earth with devastating consequences. In terms of space exploration, the Apollo 15 mission was by all accounts a resounding success. It achieved remarkable scientific and engineering milestones, pushing the boundaries of what humanity thought possible. It was the first mission to use the lunar rover, that nimble-wheeled vehicle, that gave the crew unprecedented surface mobility. This extended reach allowed for greater geological investigations, enabling them to explore more varied terrain and gather more diverse samples than ever before. They also stayed on the moon for almost 3 days longer than any crew before them, a testament to the engineering advancements of the lunar module that allowed for carrying a heavier payload. While Commander Scott and lunar module pilot Irwin were exploring the lunar surface, Worden performed the first spacewalk in deep space, venturing out into the vast, silent void between Earth and Moon. And on the lunar surface, Scott and Irwin collected the first sample of the Moon's early crust, famously known as the Genesis Rock, a fragment of ancient lunar history that offered profound insights into the Moon's formation. The crew even canceled a NASA-certified postal cover on the Moon's surface in honor of the U.S. Postal Service, a symbolic gesture of unity between earthly services and cosmic exploration. Yet, less than a year later, these extraordinary achievements, these triumphs of human ingenuity, would be overshadowed by bitter betrayal. As soon as Apollo 15 returned to Earth, the quiet agreement, the unspoken trust, began to unravel. Seeger, Eiermann, and Herrick. Those shrewd businessmen turned on their word and got to selling the postal covers. The lure of profit, it seemed, was too strong to resist overriding any promise or ethical consideration. Seeger, the stamp dealer, kept one and sold the other 99 for $1,500 each in just 2 months. Imagine the flurry of transactions, the quiet excitement among collectors eager to possess a piece of the moon. That sum in today's money would be almost $12,000 each. Herrick, the film director, also got busy commissioning sales across various dealers in New York and Europe, selling the covers for between $790 and $1,250 each, which today would be between $6,000 and almost $10,000. The covers, once mere paper transformed into sought-after artifacts, their value inflated by their illicit journey to the moon. Late in October 1971, the delicate facade began to crack. One of Herrick's interested buyers, perhaps with a touch of skepticism or a desire for absolute authenticity, contacted NASA asking if they could verify the authenticity of the cover. This simple inquiry ignited a firestorm. NASA's Director of Flight Crew Operations, Deke Slayton, the very man who had explicitly warned the crew against such actions, had no idea what he was talking about. His shock must have been profound, his frustration immense. This unexpected revelation, a direct challenge to NASA's integrity, really didn't make NASA look good. Slayton, realizing the gravity of the situation, immediately warned Worden to make sure these covers wouldn't be further publicized. He emphasized that they had only been approved under the assumption that they were for non-commercial use, a crucial ethical boundary. Worden in turn wrote to Herrick demanding he cease sales immediately. He'd later say with a poignant note of regret, "I believed Herrick was as good as his word. It was a huge lapse in judgment on my part to trust this stranger." His trust, it seemed, had been cruelly betrayed. By the next month, the news had spread like wildfire. Word about the supposed Apollo 15 covers selling all over Europe reached the American media, igniting a public scandal. The crew, who were in Germany at the time as part of their official NASA European tour, were now in a difficult position. They quietly but significantly decided it would be improper for them to accept the $7,000 promised by Seeger, a belated attempt to mitigate the ethical breach, but by then the damage was already done. The American media had gotten a hold of the news, and the story of illicit profit, rather than scientific triumph, was making headlines. Slayton was furious. His crew, the very men he had personally warned, had directly disobeyed orders. And the result was a very public dispute that deeply damaged NASA's credibility. He called the events a regular goddamn scandal, his frustration palpable. He reprimanded Irwin Scott and Worden for poor judgment, a formal condemnation of their ethical lapse. And in the most devastating blow for any astronaut, they were removed from their positions as Apollo 17 backup crew. They were stripped of their wings and never flew in space again, the ultimate punishment for those who dreamed of the stars. Their extraordinary achievements on Apollo 15 were overshadowed. Their careers in space abruptly ended by a few ounces of paper and a moment of greed. But the drama didn't end there. With the media pumping out headline after headline, there was real concern that the publicity around Apollo 15 would reduce an otherwise successful scientific mission to an unethical money grab by the crew, or worse, by NASA themselves. The reputation of the entire space program, and by extension, the nation's image, was at stake. On August 3, 1972, the Senate Committee on Aeronautical and Space Sciences held a hearing to set the record straight once and for all. It was a somber occasion, a public reckoning for a private lapse. There were several layers of concern to address. Firstly, the actions of the astronauts. The crew, now facing intense public scrutiny, acknowledged they acted thoughtlessly in not declaring the postal covers. They claimed they were oblivious to the Germans' intentions in using these covers for commercial purposes, portraying themselves as innocent victims in a businessman's game. However, something crucial had happened on board that cast significant doubt over their true intentions. At some point during the mission, the 400 unauthorized covers were moved from the main command module to the lunar module and eventually to the surface of the moon. This was a significant violation of protocol. In testimony, the astronauts agreed this violated protocol, but said they couldn't recall how or when the transfer had taken place. This was a crucial point. Postal covers usually remained within the command module. Moving them into the lunar module and then to the lunar surface would have made them a crowning jewel in a dealer's collection, increasing the value of these covers significantly. This subtle act suggested a deeper complicity, raising the question, perhaps the astronauts weren't the innocent victims in a businessman's game, as they were portraying themselves to be. The allure of higher profits, it seemed, had tempted them to cross another line. The Senate was also concerned about how NASA allowed another incident to happen so quickly after the Apollo 14 debacle. The postal covers dispute made NASA look incompetent, a vast bureaucratic entity with no idea what its employees were doing, what was being taken aboard missions, and individuals putting personal gain over the public interest of the agency. It chipped away at the image of integrity and meticulous control that NASA so carefully cultivated. Slayton himself came under fire too. Turns out, despite his rage and fury, he didn't report the crew to his superiors when he learned of the unauthorized covers. This called his integrity into question, raising eyebrows that perhaps he was somehow in on the whole operation, though nothing along those lines has ever been confirmed. Interestingly, after duress from senior NASA management, The Senate invoked a rarely used rule to close the hearing to the public when testimony might impact the reputation of witnesses or others, which in itself raises suspicions. The very act of shrouding the proceedings in secrecy, even if well-intentioned, added another layer of doubt to an already complex narrative. The repercussions of this hearing had lasting effects on NASA and their astronauts. The agency, keen to restore its tarnished image, took swift and decisive action. NASA asked all current and former astronauts to turn in any covers they had flown with, including the remaining Herrick covers and Apollo 15's 300 non-commercialized covers. This broad demand, a blanket effort to cleanse the slate, led to the suspension of 15 astronauts who had broken the faith with us and ignored a standing order from Slayton, as NASA Flight Director Christopher Kraft Jr. put it. It was a harsh, but perhaps necessary disciplinary measure to reinforce ethical standards. Today, astronauts can still carry NASA-approved personal items and mementos aboard missions, preserving a touch of personal connection to their incredible journeys. But crucially, coin stamps and postal materials that by their nature lend themselves to exploitation by the recipients are forbidden by federal regulation. This specific prohibition, a direct result of the Apollo 15 scandal, serves as a lasting reminder of the integrity breached and the lessons learned. It ensures that the symbolic value of spaceflight and the inherent trust placed in astronauts cannot be monetized in such a way again. Just when it seemed to be case closed, the record sealed, something unexpected happened. 5 years later, in 1978, the Justice Department sent a private memo to NASA, delivering a quiet yet powerful legal challenge. They informed NASA that while they likely had the right to keep all the confiscated Herrick covers, the astronauts' 300 covers intended as gifts were another matter. As these items were taken from the astronauts without any legal proceedings, NASA might have breached their constitutional rights. It was a subtle but significant legal nuance, reopening a seemingly settled case. It was on this basis, in 1983, that Worden sued NASA and won, getting the crew's covers back in an out-of-court settlement. A strange twist, a legal vindication years after the initial scandal, perhaps offering a small measure of closure for the astronauts whose careers had been so abruptly curtailed. Apollo 15 was by all accounts a successful scientific mission, a triumph of engineering and exploration. However, it was also overshadowed by a scandal that called NASA's competence into question and stained the image of the astronaut as the infallible hero. It was a human story reflecting the complexities and flaws inherent in even the noblest of pursuits. While it does seem wrong to try and profit off such a mission, some were firmly on the astronauts' side. It was perceived by some that they were being punished for behavior that wasn't new to NASA, as Shopman, an expert in stamp history, noted. Today, Seeger covers are all over the world, mainly in private collections. Only 4 ever made it to public sale, with the latest selling for over $55,000 in 2014, which would be close to $70,000 today. The monetary value, a quiet testament to the enduring allure of such illicitly flown artifacts, remains significant. Still, the questions linger, echoing softly through the years. Were the astronauts really just unfortunate pawns in an opportunistic business game, their good intentions exploited? Or were they subtly or overtly in it for personal profit, driven by the lure of the dollar? Was NASA truly oblivious to what was going on? Or were more people in on this, weaving a complex web of complicity? I don't think we'll ever truly know the full truth. This is a story that highlights how even a noble pursuit like space exploration isn't free of opportunists. Curiosity, ambition, and ingenuity are all part of human nature, shaping our grandest endeavors. But so too are wiliness and self-interest, casting their long, subtle shadows even over the stars. In that way, the story is a stark reminder of the importance of honor and honesty, personal duty and dignity in public service, and that virtues like these truly are priceless. It's a quiet whisper from the past, reminding us that the human heart, with all its complexities, journeys with us to every frontier, even the boundless void of space. Did you ever hear the story of how the Harlan J. Smith telescope got shot 7 times? It sounds like something from a whimsical, perhaps improbable tale, far removed from the quiet, meticulous world of astronomical discovery. The realm of astronomy can indeed be a surprising place, brimming with groundbreaking revelations made all the time. But normally, it's the ground beneath our feet that's being broken, metaphorically speaking, as new theories emerge, and the only shots are the beautiful captured images of the night sky. It's exceptionally rare for someone to actually attempt to attack a telescope, especially one of such grand scale. And yet, in 1970, that's exactly what happened. This moment, this act of bewildering violence, could have spelled disaster for what was then the 3rd largest telescope in the world, a marvel of engineering and scientific ambition which had only just been completed 2 years prior. What happened? Why did someone shoot through the thick glass mirror of an observatory telescope with a 9mm pistol at point-blank range? And perhaps even more astonishingly, how did a glass mirror of such impressive size and meticulous construction deal with 7 shots from a gun, and even before that, several preliminary strikes from a hammer? These are questions that defy common sense, beckoning us to understand a unique and perplexing incident in the annals of science. In 1963, as the space race was just beginning to truly capture the world's imagination, a different kind of ambition was stirring on Earth. NASA was considering how best to visit the planets of the solar system. This was a grand, daunting task, requiring not just rockets and spacecraft, but a deeper understanding of those distant worlds. As part of the US's overarching goal to get ahead of the Soviet Union in this cosmic race, more information, more detailed images, and more precise data about the planets were desperately needed. And so, with a clear purpose, NASA started planning new telescopes that could image the heavens with unprecedented clarity, turning their gaze outward to pave the way for human voyages. It was into this exciting yet demanding scene that Harlan J. Smith quietly stepped. Smith was a driven man described as softly spoken by his peers, yet possessing a deep love of astronomy. He had just been made director of the McDonald Observatory, a revered institution operated by the University of Texas and nestled high in the mountains near Fort Davis, Texas. In his very first official act as director, a testament to his vision and persuasive power, he was able to persuade NASA to give $5 million to build a new telescope on his site. It was a substantial sum, a powerful endorsement of his vision. The project, imbued with fresh purpose and funding, went ahead, and production began in 1964 and was completed in 1968. This was no small undertaking, no mere instrument to be assembled lightly. The newly finished 2.7-meter mirror telescope was at that point in time the 3rd largest in the world. Imagine the sheer scale of it, a monumental achievement of optical engineering. It was a beast of an instrument, weighing in at 160 tons, a massive yet delicately balanced mechanism. Its light-gathering capabilities were staggering 250,000 times greater than was viewable with the human eye. It was like opening a cosmic aperture, allowing humanity to drink in the faint, distant light of the universe with an intensity never before possible. Usually, while the electronic components of a telescope, the intricate circuitry that powers its modern functions, can be changed out as technology improves. The telescope's expected lifespan is remarkably long, about 100 years. This longevity is incredibly useful, as often observations can take decades to complete. For instance, it can take 20 or so years for some known exoplanets to complete one full orbit, and undiscovered ones could potentially take even longer. This new grand telescope was designed to be a durable sentinel watching the cosmos for generations. The newly built telescope was envisioned as something of a Swiss Army knife for astronomers capable of a wide range of observations. But its primary focus would be on spectroscopy, the delicate art of analyzing light to understand the chemical composition, temperature, and motion of distant celestial objects. The heart of this mighty instrument, the very piece that allowed it to perform its cosmic magic, was its mirror. The mirror itself was made of fused silica glass, a material chosen for its exceptional properties. And while you might think that sounds easy enough to make, we create glass all the time, right? For windows and bottles fused, silica is a special kind of glass that's made in a very particular technically involved way. Imagine the immense effort the process of producing the fused silica for that mirror took almost 1.5 years piece by carefully crafted piece. It involved a complex procedure of plasma torch hydrolysis using silica gas that required temperatures of 1700 degree Kelvin. And after the subsequent 1 to 400 degree Kelvin process that fused its segments together was complete, the delicate, slow art of cooling began. Just cooling the entire shape back down again to take its final form took another 2 years. This meticulous, painstaking process was all undertaken to create a mirror that had almost zero internal stresses and strains, a perfect unblemished surface for the incredibly precise work ahead of it, which is precisely why it was so utterly serious, so profoundly unsettling, when not even 2 years later, a man named Jack Hyde decided to try and take the observatory's telescope mirror out of commission. The audacity of the act, the seeming senselessness of attacking such a marvel of science, must have sent shockwaves through the quiet astronomical community. Jack was an instruments technician who had only recently come to work at the McDonald Observatory starting on January 1st, 1970. And as for his motivations, those remain shrouded in a frustrating mystery. We don't completely know his motivations. We know some fragments of his story. He was in his 30s, had previously been employed at the prestigious Smithsonian Observatory in Massachusetts, a highly respected institution. He had traveled to Texas to work at McDonald, while his wife and 3 children went to live in Nebraska, a separation that might have weighed heavily on him. The McDonald Observatory itself, nestled high up in the remote Davis Mountains, offered a stark beauty, but also a profound isolation. Its elevated position meant it had little light pollution and less atmosphere to contend with, making it ideal for astronomical observations. The nearest town, Fort Davis, was around 27 kilometers away, a considerable distance, meaning that all the staff tended to live on site. This communal yet isolated living arrangement, while fostering a unique camaraderie, might also have exacerbated feelings of loneliness for someone already struggling. Such isolation and distance from his family may have taken a psychological toll on Jack. And on top of that, the hours at an observatory were notoriously long and demanding. Observatories always want to be performing science as much as possible when conditions are right, chasing fleeting moments of clear skies. This sometimes meant technicians and operators could be pulling 48 or even 72-hour shifts, working around the clock when the cosmic conditions aligned. This isn't entirely surprising, of course. Bad weather, too high atmospheric dust levels, or strong 100 km/h winds could call a halt to the telescope being used at all, making clear nights precious. And if you work in an observatory, you are likely passionate about astronomy, driven by a deep love for the cosmos. But when you combine the isolation from family with the grueling high-pressure hours, perhaps it sheds some light on why Jack Hyde, just a month after starting work, showed up to the telescope observatory at midnight with a hammer in his hand and a 9mm gun in his pocket. There are reports that Mr. Hyde had been drinking that night, adding another layer of impairment to what was clearly a deeply troubled state. And it is also suggested that he was suffering from bad mental health, a silent battle waged within that ultimately spilled out in a devastating act. On the night of February 5th, a date etched into the observatory's history, most of the staff were asleep in their on-site accommodations. The number of people manning the McDonald Observatory was never that high in those days, particularly in the quiet hours of the night. But only 1 telescope operator and 1 supervisor were actually in the building at the time of the incident. Their presence, a testament to the continuous vigil kept over the cosmos, placed them in immediate unforeseen danger. Mr. Hyde entered the building with relative ease. He worked there, after all, his face and presence familiar to the few night staff. And crucially, There had never been a problem like this before. No reason for heightened security or suspicion. So there was little to stop him. He quickly found the supervisor, and in an act of sudden, inexplicable violence, fired a shot directly at him. Miraculously, fate or perhaps sheer luck intervened. Although the bullet went through the man's clothes, it thankfully passed through without hitting him directly and impacted the wall behind him. The supervisor, understandably terrified and acting on pure instinct, ran off to get help. His cries for assistance echoing through the quiet observatory halls. Hyde then turned his attention to the remaining telescope operator, and under the terrifying threat of the gun, got him to lower the telescope into a maintenance mode. This was a critical step, rendering the mighty instrument vulnerable, making its precious mirror easily accessible. With the telescope now in a position of quiet submission, Hyde entered the massive structure, the heart of the observatory, and got out his hammer. He approached the gleaming polished surface of the mirror and struck it, expecting it to shatter. He was an instruments technician, meaning he usually dealt with the delicate image-capturing camera and equipment at the bottom of the telescope. He was thus unfamiliar with the unique properties of the glass mirror, a material unlike any other. And to his surprise, perhaps even his frustration, his hammer did not smash the 4.5-ton mirror into a million fragments. Instead, it bounced off, recoiling violently and hitting him instead. He did, however, manage to chip off a pear-shaped dent from the mirror, a small permanent scar, but that was about it. In a fit of mounting frustration and desperation, Hyde then pointed his gun at the mirror and unloaded all 7 remaining shots in his clip. Each one fired at point-blank range, lodged into the mirror, but did little more than penetrate a few centimeters. The remarkable resilience of the mirror was a testament to its extraordinary construction. The process of making the mirror had involved taking layers of glass and fusing them on top of each other. This was due to the scarcity of the fused silicon material, and because of other limitations of the technology at the time, it was easier to make smaller pieces and fuse them together. But ironically, this meticulous layered process had created a material similar to laminate glass. Combined with its impressive thickness of 31.8 cm, almost 12.5 inches, it was essentially bulletproof. A marvel of accidental defense, born from engineering necessity. By this point, more staff alerted by the supervisor's cries and the unsettling sounds arrived on the scene to restrain Hyde, holding him until the local sheriff arrived to take him into custody. Unfortunately, when the sheriff looked at the mirror, he mistakenly thought that it was completely destroyed due to the large hole in its center. He didn't realize, in his understandable lack of astronomical knowledge, that the central hole was supposed to be there, designed for instruments and light paths. It was just the smaller bullet holes that were the actual problem, the subtle wounds on an otherwise functional giant. Newspapers, eager for sensational headlines, began running stories about how the telescope was destroyed, a tragic end to a scientific marvel. And so, Harlan J. Smith, the director, the very man who had championed its construction, had to publish an official report, a quiet, reassuring message telling the astronomical community that there was actually nothing to worry about. The telescope, miraculously, was largely intact. Ironically, Hyde's shots had mostly missed the vital part of the mirror. To an untrained eye, all parts of a telescope mirror look like they serve the same function, contributing equally to the image. However, the portions of the mirror near to its center are actually largely unused for resolution, as they are shadowed by other components and perhaps are only used for a little light gathering. It's the area near this critical ring closer to the outer edges that truly gathers the light used in imaging. Fortunately, this meant that only 3 of Hyde's shots actually hit a critical area of the mirror. And even then, given that those small centimeter-wide holes only contributed to a small fraction of the mirror's total surface area, Mr. Smith was able to report that the bullet holes reduced the light collecting efficiency by about 1% and introduced a very small amount of diffraction, a minimal impact on its cosmic vision. Not only was the telescope able to survive the attack, it actually came out almost completely unscathed, a testament to its robust design and a stroke of cosmic luck, Mr. Hyde initially faced the prospect of criminal charges with a potential jail sentence of 2 to 20 years, a severe punishment for a severe act. But when Director Smith learned about the mental health problems Mr. Hyde had been facing, the quiet struggles that had perhaps led to this explosive outburst, he made a compassionate decision. He decided not to press charges. Instead, he elected to get Mr. Hyde into a mental institution and tried to get him help. It was a remarkably kind act, an indication that the director didn't harbor any actual ill will towards Hyde, perhaps because, fortunately, no real harm had been done to either man or machine. However, when he was eventually released, Mr. Hyde did not return to work at the observatory. His connection to the stars and to that particular instrument was severed forever. The University of Texas engineers responsible for maintaining the mirror didn't need to do much to repair it, a testament to the mirror's inherent resilience. Using a small drill, they carefully bored out the bullets and smoothed out the holes to prevent any further cracking. Then they simply layered the reflective surface back on and called it good. To be fair, nothing further was required. The damage was superficial, the core integrity of the mirror untouched. The Harlan J. Smith telescope still bears these bullet holes to this day, a silent, almost invisible testament to that bizarre night, a unique set of battle scars from a forgotten conflict. The telescope, despite its brief brush with human violence, went on to have an illustrious career. Its powerful gaze, unimpeded by those small wounds, helped inform the plans for the Voyager missions, those intrepid robotic explorers that ventured to the outer reaches of our solar system. And it has also made huge discoveries in the field of exoplanet research long before the current boom in that field. Back in an era when people had no idea exoplanets were even out there in any significant number, the Harlan J. Smith telescope searched the skies for these astronomical bodies, helping confirm that they are so frequent that every star might have at least one. It was a pioneer expanding our understanding of planetary systems beyond our own. So the science community is profoundly grateful that Mr. Hyde didn't manage to carry out his objective. At the time, science would have lost much without this telescope, which later was justly named the Harlan J. Smith Telescope in honor of the director who had built it, a testament to his vision and his compassionate leadership. But fortunately, it has suffered little more than a few battle scars from that night over 50 years ago that it can show to curious observers like you and I. And to be fair, when it comes to battle scars, it still has an easier time of it than space telescopes like the James Webb, which face the ever-present threat of micrometeorites striking its mirrors. The cosmos, in its quiet indifference, presents its own challenges far more relentless than a human with a gun. So how does a telescope deal with a 9mm pistol? Pretty well is the answer, surprisingly, thanks to excellent engineering and about 4 tons of bulletproof glass. The more you know, the more you realize the quiet wonders of human ingenuity and the unexpected resilience of our creations. A big thanks to Coyne Gibson, the McDonald Observatory's present-day manager of observing support, who was able to speak to me and provided me with a lot of these photographs. He helped make this script possible, bringing the silent story of a shot telescope to light. And as we allow these images of resilience and quiet human drama to settle, let us turn our gaze to another tale, one that explores the very beginning of human-like ventures into the vast unknown. It's a story of a pioneer, not human, but a trailblazer nonetheless, whose journey set the course for years of human space exploration. It is the story of Ham the chimpanzee, a very special being, the first hominid in space. Ham the chimpanzee was indeed very special. He was more than just an animal. He was a trailblazer, a pioneer who in his own quiet way set the course for years of human space exploration. Imagine the immense weight of expectation, the hopes and fears of an entire nation resting upon the small shoulders of a creature who knew nothing of geopolitical races or scientific ambition. So, what was his story? Did he survive the pioneering journey, a voyage that took him further from Earth than anyone had ever gone before? I'm Alex McCone, and you're watching Astram. And together, we will recount the story of Ham the chimp and the profound legacy his mission left behind. The tale of Ham, and indeed of much early American space exploration, is deeply rooted in Project Mercury. This grand endeavor came about as the direct result of the fierce space race between the USSR and the USA. Both countries, locked in an intense, silent competition, were furiously trying to be the first ones in space. This wasn't merely about bragging rights. It was understood as a profound display of their military powers against the other rival nation. A successful space launch was a potent symbol of advanced rocketry and technological prowess with chilling implications for intercontinental ballistic missiles. This ambitious program, Project Mercury, is also the very foundation from which NASA was founded, rising from the ashes of earlier fragmented military efforts to become the unified force behind America's space dreams. Before Project Mercury took center stage in the early 1950s, space-related endeavors were primarily performed by the U.S. military. Their initial approach was cautious, yet determined. They initially sent mice and monkeys into space to test the profound unknown effects of rocket travel. Imagine these small, unsuspecting creatures launched skyward to experience huge G-forces, the immense pressure that pushes you back into your seat during a powerful acceleration, and the eerie sensation of weightlessness that comes with breaking free from Earth's embrace. These animal pioneers were crucial for understanding the basic physiological responses to spaceflight before risking human lives. The rockets themselves in those nascent days were very basic, almost rudimentary by today's soaring standards. Take, for instance, a rocket called the Aero B-3. It was pretty small at only 8 meters tall, a slender spire against the sky. And in this particular test, it reached altitudes of only 60 kilometers, a mere whisper, compared to later orbital flights. Yet for the small beings inside, it was a profound journey. They experienced 4 Gs on takeoff, a force pushing them back with 4 times the weight of their own bodies, and then the blissful, disorienting experience of weightlessness for a few minutes. The animals inside the rocket appeared perplexed by their journey, perhaps a little disoriented, but crucially, they survived the trip with no apparent harm or after effects. Their resilience offered a glimmer of hope that humans, too, might endure such a voyage. Monkeys were specifically chosen during this time because they closely matched the physiology of humans. It was thought with logical precision that whatever happens to them would be a good indicator of what would happen to a human in space. They were living proxies sent ahead to brave the unknown. One of the last space missions of the U.S. military before NASA fully took over was in 1959. In a notable success, they successfully launched 2 monkeys, Miss Abel and Miss Baker, into space at an altitude of 570 kilometers on board a Jupiter rocket. On this truly remarkable trip, they withstood a maximum of 38 Gs, an immense crushing force, and reached a top speed of 16,000 km/h. It was a testament to the sheer power of the rockets and the surprising endurance of these small travelers. The mission was by all scientific measures a success. The nose cone was successfully recovered, bringing the precious cargo back to Earth. But unfortunately, a poignant note of sadness followed. Abel died a few days after the flight, after having surgery performed on her unsuccessfully, a reminder of the fragility of life even after a triumphant journey. Miss Baker, on the other hand, lived a good while after the flight, defying expectations. She was even able to breed as part of tests on her reproductive organs, offering valuable data for future human reproductive health in space. She was honored for her contributions to scientific discovery, a silent hero in the annals of spaceflight. Even today, a touching tribute remains. Bananas can be found on her grave in respect to her accomplishments, a gentle nod to her species, and her quiet sacrifice. A few months after this pioneering flight, NASA, with Project Mercury, took over the monumental goal of bringing humans to space. They now had a new set of rockets at their disposal, including the more powerful Mercury Atlas and the Mercury Redstone. America, however, was under immense pressure by the Russians, who had already claimed the critical firsts. They had been the first ones to get a satellite into orbit in 1957, launching the famous Sputnik 1 with its persistent, unsettling radio transmission. After a couple of years of testing these new Mercury rockets, meticulously refining their capabilities, NASA felt by 1961 that they were finally ready to send a hominid or great ape into space aboard a Mercury Redstone rocket. This Mercury Redstone rocket was considerably bigger than the earlier Aerobee, a more substantial pillar of steel and fuel at 25 meters long. Yet it was still much smaller than the colossal rockets of today, mere whispers, compared to the giants that would follow. It was, however, big enough to fit a human in the capsule at the top, a crucial step towards the ultimate goal. The Mercury Redstone rocket was only capable of suborbital flight, though meaning it would reach space arc through the void, but not be able to stay in orbit around the Earth. It would ascend, experience space, and then return a giant leap, but not yet a continuous presence. The choice of candidate for this mission was profoundly important. Unlike the earlier animal flights in this case, the chimp would not just be a passenger, a passive observer of the forces unleashed. It would be required to perform tasks while in space. This was a critical step designed to prove that a complex organism, a being with cognitive abilities, could function under the alien conditions of microgravity. The ability to perform tasks while in the capsule would pave the way for human astronauts in the future, proving that human minds could remain alert and functional. It meant human astronauts would not have to totally rely on automation should the rocket lose contact with the command base, for whatever unforeseen reason, offering a crucial layer of redundancy and control. From a pool of 40 chimpanzee candidates, a careful and extensive selection process began. Imagine the diligent observation, the quiet assessments of these intelligent creatures. Ham was eventually chosen through a series of selection processes, including selecting the healthiest chimp and the one that followed commands best. He was also picked because he was a particularly happy chimp with a good temperament, a crucial quality for enduring the stress of such a pioneering journey. At this point, Ham was only known as number 65. This anonymity was a grim, pragmatic decision. The U.S. didn't want the bad press associated from a named chimp dying should the mission fail. It was a cold calculation prioritizing public perception over individual identity. Ham, the quiet pioneer, was then meticulously trained for his role. He was taught to pull a lever within 5 seconds of seeing a blue light. This was his primary task, a simple yet critical test of his cognitive function and responsiveness in a novel environment. If he performed correctly, a reward followed. He would be rewarded with a banana pellet, a sweet encouragement in the face of the unknown. Should he not pull the lever within the allotted time, a mild deterrent was employed. He would receive a mild electric shock in his foot. It was a basic operant conditioning, a method to ensure compliance and gather reliable data on his performance under stress. After months of these rigorous preparations, Ham was finally deemed ready for the flight, his small body and keen mind conditioned for the grand voyage. They inserted him into a mini capsule at first, as a form of a spacesuit for the chimp. This custom-made enclosure was designed to be his immediate personal sanctuary in the harsh environment of space. This mini capsule would meticulously control pressure, oxygen, and temperature for Ham, creating a stable, breathable microenvironment within the larger rocket. He was also equipped with an array of sensors measuring his vital signs, tiny electrical pulses and bioreadings that constantly communicated this information back to ground control on Earth, thanks to the rocket's antenna. His arms were left free in order to perform the commands he was given during the flight, allowing him to interact with his console. And he even had a window so he could see what was going on, offering him a limited yet profound view of the unfolding cosmos. The time for the launch approached a crescendo of anticipation and last-minute checks. Many scientists and engineers worked tirelessly, their faces etched with concentration, doing their utmost to ensure everything went well with the flight. Every wire, every circuit, every drop of fuel was scrutinized. Ham was then placed into the main capsule of the Mercury Redstone rocket for launch. This main capsule, much larger, was also pressurized, as this was where the human astronaut would eventually sit should this mission go to plan and prove the concept viable for human flight. As the morning came, the mighty rocket launched a fiery assertion of human ambition against the sky. But almost immediately, the carefully orchestrated ballet began to go awry. After only 1 minute into the flight computers on board, the rocket communicated back to command that the flight plan angle was already 1 degree too high and rising. A subtle deviation, yet one with profound implications. This steeper angle meant the rocket accelerated a lot faster than planned, pushing the boundaries of its design. With predicted G-forces reaching a staggering 17 Gs in the capsule for poor Ham, it was an immense, unexpected crushing force, far beyond what was anticipated. After just 2.5 minutes, the liquid oxygen for the rocket was depleted, a critical failure in the propulsion system. This sent a chilling mayday signal to recovery forces, a silent cry for help echoing across the networks. The rocket, now unstable and shedding its power, was spinning wildly, veering off its intended course. It was a lot higher than expected and had achieved higher speeds than anticipated, a powerful beast, now out of control. As a response to this escalating crisis, an abort signal was sent, a desperate attempt to save the precious cargo within. The capsule was ejected early from the rocket at an altitude of 250 kilometers instead of 185 kilometers, jettisoned prematurely from its wild ascent. This early abort meant that there were no retro-rockets to slow the descent, a crucial mechanism for a controlled return. And so, the capsule containing Ham, now a lone projectile, hurtled back towards Earth at immense speed, subject only to the relentless pull of gravity. If this wasn't enough compounding, the perilous situation sensors reported that the main capsule was losing pressure fast. This alarming reading, a terrifying drop in life-sustaining air, later turned out to be caused by a faulty air inlet snorkel valve, a small critical component whose pin came loose after vibrations from the launch. A tiny mechanical failure triggered by the immense forces of ascent now threatened the entire mission. At this point, though, in a curious twist of fate, Ham was blissfully unaware of all these problems going on around him. His mini capsule, that carefully designed inner sanctuary, proved to be his salvation. It meant that he was unaffected by the falling pressure in the main capsule, cocooned safely within his own sealed environment. He was, in fact, happily playing the lever and lights game, absorbed in his conditioned tasks, performing only marginally slower than his results on Earth. His small world inside the capsule remained stable even as the larger world around him plunged into crisis. As the capsule began its re-entry back into Earth's atmosphere, the forces of deceleration began to assert themselves. Ham was again subjected to higher G-forces than expected, this time 14 Gs, as the capsule slammed into the thicker layers of air. Because there were no retro-rockets fired to slow descent, the capsule had overshot its expected landing area by 100-kilometer landing, far off course in the vastness of the Atlantic Ocean. Finally, the capsule's parachutes deployed, blossoming into bright canopies against the sky, and airbags around the base were inflated to cushion the fall and help with floating on the water's surface upon impact. Color dye was released into the sea to help aid recovery, a vivid stain against the deep blue marking the spot for rescue crews. It wasn't until 12 excruciating minutes had passed before the capsule sent its first recovery signal, a faint but hopeful electronic whisper across the waves. And then, 27 minutes after landing, a search plane finally spotted the capsule floating in the Atlantic, a small bobbing speck against the vast ocean. The U.S. Navy rescue helicopters were swiftly sent from the nearest ship to pick up the capsule. But by the time they got there, a new problem had emerged. The capsule had taken in water and was quickly submerging. The immense impact from the landing had popped off the heat shield at the base, puncturing holes into the base of the capsule. The airbags designed to provide flotation were heavily worn and failing, and that leaky snorkel valve from earlier, the tiny culprit, was also allowing water in. By the time the capsule was rescued, a full 360 kilos of water had flooded on board, threatening to drown its precious cargo. After a grueling 3-hour recovery operation, during which every minute must have felt like an eternity, the capsule and its precious cargo were finally airlifted to the nearest Navy ship. There, a group of anxious NASA scientists waited on hand to see the fate of Ham. A lot had gone wrong with this mission, far more than anticipated. The rocket had gone off course, the G-forces were higher than predicted, the parachute descent was uncontrolled, and the capsule was taking on water. But was he still alive after all of that? And if so, what state was he in? Scientists and Navy personnel worked quickly, their movements precise and urgent to get him out. The cover came off, revealing the small chimpanzee inside. And then a wave of relief must have washed over them. Ham was fine. He had done it. He was safe and well. Still his happy self, almost as if nothing noteworthy had happened. He had survived everything, this small, resilient pioneer, relatively unscathed. His only injury was a bruised nose, a minor mark from a journey of immense peril. It was a miracle, a testament to his endurance and the robust design of his mini capsule. Ham retired from spacefaring shortly thereafter, his pioneering mission complete. He lived a good 20 years after his voyage in a number of zoos, a celebrity in his own right, admired for his quiet courage. He passed away in 1983. His skeleton was sent to the U.S. National Museum of Health and Medicine, a scientific artifact forever preserving his contribution to human knowledge. His other remains were buried and honored by the International Space Hall of Fame in New Mexico, a fitting tribute to his place in history. Because of the success of this mission, despite all its harrowing moments a few months later, the U.S. successfully sent Alan Shepard into space on board another Mercury Redstone rocket called Freedom 7. It was a crucial step, proving that a human could indeed endure the rigors of spaceflight. However, the U.S. didn't ultimately win this particular leg of the space race. The Soviets, with their relentless drive, had already secured the ultimate prize. They had successfully orbited around the Earth, with a human on board Yuri Gagarin aboard Vostok 1. But the legacy of Ham's mission, and indeed of Project Mercury, can still be felt today. The path they paved, the knowledge they gained, laid the groundwork for all that followed. With humans now aboard the International Space Station, a permanent orbital outpost, and even now with a renewed space race to get humans on the moon a second time, the echoes of those early animal pioneers continue to resonate. Ham, the chimpanzee who beat all humans to space, remains a quiet testament to the bravery, the ingenuity, and the occasional good fortune that defines humanity's ongoing journey into the boundless frontier. His story is a gentle whisper, a reminder of the small steps that lead to giant leaps and the unexpected heroes who sometimes lead the way. If I were a superstitious man, I would advise you to be careful what you call your space missions. There's a subtle, almost poetic resonance in names, a whisper of destiny, perhaps. When Russia, in a renewed burst of ambition, named its first mission to the moon, in 47 years, it was originally given the designation Luna Glob, translating in English to lunar sphere. It carried a sense of vastness, of cosmic reach. However, this name troubled the scientific director of the Space Research Institute of the Russian Academy of Sciences, Lev Zeleny. For in the subtle nuances of language, glob was too similar to a different Russian word, grob, meaning coffin, a chilling phonetic echo, a dark premonition. Zeleny, perhaps sensing this unsettling resonance, wisely changed the name of the mission to Luna 25, intending to call back to the earlier successful Soviet Luna missions, which were the last time Russian spacecraft successfully landed on the moon. It was an attempt to invoke past glories, to draw a line of continuity from a triumphant era. But perhaps it was too late, and something of that original name, that haunting whisper of grob, lingered, for we now know that Luna Coffin was a much more apt name for the ill-fated Luna 25. I'm Alex McCohen, and you're watching Astrum. Join us today as we explore the fate of Russia's first moon mission since 1976. For the country that once led the world in the space race, what exactly went wrong? Although we often look at NASA or ESA missions here at Astrom, Russia's space program has historically been quite the powerhouse, a titan in the early days of cosmic exploration. Back when Russia was part of the USSR, it was the Soviet Union's launching of Sputnik 1, the very first artificial satellite that truly triggered the space race in 1957. It was a single beeping sphere, yet it sent shockwaves around the world, igniting a competition that would define an era. And for a time, the Soviet space program went from strength to strength, achieving a series of remarkable firsts that seemed to put them far ahead in the cosmic sprint. It was the Soviet Union that put the first man into space, Yuri Gagarin, a feat that captivated the entire planet. They also sent the first woman, Valentina Tereshkova, breaking another invisible barrier. They had the first multi-person crew demonstrating complex orbital operations. And in a more unusual but no less pioneering effort, they sent the first dog into space, Laika, a silent, furry pioneer. Their rockets were the first to escape the Earth-Moon system, the first to impact the Moon, and the first to orbit the Moon, mapping its hidden far side. Soviet cosmonauts performed the first spacewalk, a daring ballet in the vacuum, and the USSR even launched the first space station, a prototype for humanity's permanent presence in orbit. To the eyes of many, and certainly to the immense pleasure of Soviet leadership, the USSR was winning the space race. But beneath that glittering surface, not everything was going as smoothly as it appeared. The Soviet Union also bore the grim distinction of seeing the first death during a space mission when cosmonaut Vladimir Komarov's re-entry capsule's parachute failed to open on his re-entry to Earth. A tragic reminder of the inherent dangers of this new frontier. And later, the only 3 men to have died in space were a crew of Soviet cosmonauts tragically lost during a visit to that first ever space station. It became apparent that Soviet launches were plagued with failures, a hidden truth behind the celebrated successes. But eager to look good in the eyes of the world, particularly compared to its fierce rival, the USSR simply didn't report any of its failed lunar missions. It pretended any rocket that didn't make it out of the atmosphere was never intended to be a moon mission at all, a quiet erasure of failure from the official narrative. In reality, only about 34% of Soviet moon missions ended in success, a stark contrast to America's 60% success rate on equivalent missions. Then the turning point arrived. America landed the first man on the moon in 1969, a monumental achievement that captured the world's imagination and effectively sealed the primary objective of the space race. After that crowning achievement, both superpowers seemed to lose interest in continuing the race to the moon, their attention and resources shifting towards non-lunar pursuits. By the mid-1970s, Soviet cosmonauts never set foot on the moon itself. The USSR canceled any of its plans to do so, as the endeavor was ultimately seen as too expensive, a colossal undertaking that no longer justified the cost once the primary victory had been secured by their rival. Perhaps more importantly, what was the point of going if you were only going to get there second? But with the turn of the millennium, and since the fall of the Soviet Union in 1991, the world's interest in going to the moon has been rekindled. Scientists realized that the moon would make a good stepping stone for human space missions to Mars, a logical next leap in our cosmic journey. This is largely due to its plentiful resources, such as newly discovered water ice, which is ideal for rocket fuel, as well as potential sources of air and water for future habitats. And its low gravity makes it an excellent staging ground for launches to deeper space. Lunar resources also began to attract the attention of businesses, for economic reasons, seeing the potential for profit from lunar mining and infrastructure. And nations began to consider setting up permanent bases on its surface as a way of turning a profit and asserting their presence. And of course, there is still a lot of science to be done there, attracting those who wish to learn more about the processes by which the moon formed and the intricate cycles that govern it. Russia, keenly aware of this renewed global interest, did not intend to be left behind. It was eager to pick up the Soviet legacy of space exploration, to reassert its prowess in this new era. In fact, it beat its competitors to the punch in a way. Russia had already begun thinking about a new lunar mission as early as the mid-1990s, when scientists Mikhail Mavrov and Eric Galimov put forward their proposals to Roscosmos, Russia's newly restructured space agency. Their Luna-Glob mission was approved and was initially intended to have a lot more parts to it, including a penetrator for seismic sounding a lander and an orbiter. It was a comprehensive vision, a grand return to lunar exploration. However, the project initially did not have enough political will behind it. It faced budget cuts after the Russian financial crisis of 1998, when the ruble lost over 2/3 of its value in just 3 weeks, plunging the nation into economic turmoil. And it was marred in delays that repeatedly knocked it back and put it on hold. The ambitious penetrator and orbiter components were eventually scrapped, leaving just the lander as the plan for the mission was reimagined to make it more economical. Russia wanted to be a nationally recognized player in the space game, to stand shoulder to shoulder with other spacefaring nations, but didn't want to spend massive amounts of its budget on the plan. In 2005, for instance, Russia only invested 20 billion rubles, or about $700 million US, in its space industry, a tiny fraction compared to the USA's $15.6 billion. One way to work around this budget constraint was to collaborate with other nations. Russia initially tried to work with India on the Chandrayaan-2 mission in 2007. The plan was for Luna 25 to fly with India's orbiter and be the mission's lander, a cooperative effort to share the burdens and the glory. However, this low spending ultimately punished them. Russian scientists were unable to get the lander's technology working in time for the initial 2013 launch date. India, facing these delays, eventually abandoned the collaboration and completed Chandrayaan-2 on their own. Russia was left trying to get Luna 25 to the moon surface solo, a testament to the challenges of underfunding in ambitious space projects. India's Chandrayaan-2 lander, in its own attempt, tragically crashed into the moon. But India, resilient and determined, was eager to try again with Chandrayaan-3. This set Russia and India on a new course, from collaborators to unexpected competitors. Both Russia and India were particularly interested in the moon's south pole, a region where Chandrayaan-2 and other missions had confirmed through spectrometry the presence of water ice. This ice, locked away in permanently shadowed craters, holds immense promise for future human missions. Luna 25 and Chandrayaan-3 were now racing to be the first lander to successfully touch down on the moon's south pole and potentially discover that vital water ice, a silent, high-stakes sprint for a precious cosmic resource. However, Russia faced a new formidable problem that cast a long shadow over its space ambitions: the invasion of Ukraine in 2022. Western countries were outraged at Russia's decision to attack its neighbor and came together to impose massive sanctions. Not only was this painful economically, but one vital element of these sanctions was a ban on the trade of high-end computer chips and components. These critical technologies were designed to prevent Russia from developing high-precision ballistic rockets for use in its military, but they also severely hit Russia's lunar goals. European scientists began ending their collaborations with Roscosmos, suddenly severing crucial ties. In an interconnected world where Russia traded for much of its high-end components, Russia would now have to go it alone, a stark and immediate consequence of its geopolitical actions. India, moving with characteristic determination, completed Chandrayaan-3 and launched it on July 14, 2023, a mission we covered in greater detail in a previous video. However, the route that they took to the moon was a fuel-efficient but time-inefficient one. It would take over a month to actually arrive on the moon's surface, a slow, methodical journey. India estimated a touchdown date on August 23rd. This left a window for Russia. If Russia really hurried, if it pushed its capabilities to the limit, it could complete its lander and arrive before India by taking a shorter, more fuel-intensive route using Russia's powerful Soyuz 2.1B rocket. The Luna 25 mission had by this time already been delayed from 2021 to 2022 and then to 2023. In a final unfortunate stroke of bad luck for Russia, its BIB navigation sensor didn't pass quality tests. This was problematic critically. So as the BIB sensor relied on a computer chip normally supplied from the West, a chip that Russia could no longer purchase due to Western sanctions. And so Russian scientists had to develop a new one on their own, a testament to their resilience, but also to the immense pressure they were under. The BISL Luna 25 was cleared as ready to launch on August 11, 2023. It had 8 Russian scientific instruments on board, a comprehensive suite of tools designed to study the lunar environment. These included laser mass spectrometers, infrared spectrometers, cameras for imaging the lunar surface, and even a device for measuring dust and micrometeors. Luna 25, if successful, would operate on the moon's surface for a whole year, enduring the freezing cold of lunar nights and the intense solar radiation of lunar days. It had the potential to do some truly good science. The Soyuz rocket, powerful and reliable, was robust enough that it would get Luna 25 to the moon surface by August 21st, a full 2 crucial days before India's lander arrived. Russia would indeed win the race against its rival, achieving a symbolic first in this renewed lunar sprint. Luna 25 launched successfully from the Vostochny Cosmodrome on August 11, 2023, a powerful, triumphant ascent. It entered the moon's orbit on August 16, a critical milestone achieved. It even took photographs of the moon's surface, imaging the Xene crater, a testament to its operational capabilities. All systems were functioning normally, and communications were good. A collective sigh of relief for the Roscosmos team. Russian scientists then began to make final preparations for the landing itself. The south pole of the moon is home to some treacherous terrain, a rugged landscape of craters and shadows, and the scientists didn't want a rough touchdown, which could potentially harm Luna 25 and its delicate instruments. But then, something went terribly wrong. On August 19th, Luna 25 lost communications with Earth. The vital link, the constant stream of data and commands, was severed, no longer guided remotely. Luna 25 attempted to perform its own pre-planned maneuver, a critical step that would take it from a circular orbit around the moon into the new elliptical path down towards the surface. However, further failures occurred, cascading one after another. The BISL navigation device, the very one developed by Russian scientists, after the previous Western-supplied one hadn't passed quality control tests, had sent bad information to the ship's onboard control unit. It was a fatal error, a small miscalculation with catastrophic consequences. As a result, the thrusters, instead of firing for the intended 84 seconds, fired for an agonizing 127 seconds, propelling Luna 25 with uncontrolled force. This propelled the spacecraft into a steeper and steeper descent. On the 20th of August, Luna 25 careened down towards the moon's surface at a pace too fast to stop. Roscosmos scientists watching from millions of miles away could do nothing but look on in horror as the lander hurtled towards the terrain, traveling faster and faster. Although no external cameras witnessed the impact, it's easy to imagine the grim result of acceleration under gravity that turned Luna 25 back into a lunar coffin. Its Luna mission had not lasted a year, but only a few days. NASA's Lunar Reconnaissance Orbiter did a flyby later, a silent observer from above taking an image of the site of the craft's final resting place. Luna 25 had impacted hard, creating a crater about 10 meters in diameter, a stark permanent scar on the lunar surface, a silent tomb for a shattered ambition. Russia had attempted to show the world that it was still a great power when it came to space exploration, that its legacy from the Soviet era still burned brightly. However, Luna 25 had been mired by pressures and challenges. Western sanctions had indirectly sabotaged it, forcing a reliance on unproven domestic technology. The Russian replacement chip was not precise enough, Or perhaps was not hardy enough to survive the high radiation environment of space, a subtle yet fatal flaw. However, Russia's attempt to beat its rival India had also created problems for itself, contributing to the ultimate failure. When I learned about its arrival date being 2 days before India's, it reminded me of a similar time when the Soviet Union's Luna 15 mission crashed into the moon only a few hundred miles, and on the same day as Apollo 11 landed. Luna 15 had been tasked with collecting moon rocks, the same as the astronauts of Apollo 11. And although it was unmanned if America's mission had failed, it would have been a point of pride to the Soviet Union that Luna 15 had managed to steal Americans' thunder. This was political point, scoring a desperate need to claim any victory in the space race. The Soviet Union didn't want to just get to the moon. It wanted to get there first. And inevitably, when you're racing to beat someone else, you often take less time making sure everything works as well as it needs to. And so, you run a greater risk of failure. Ultimately, just like with Luna 15, Russia's Luna 25 had the opposite effect that its country's leadership intended. Rather than show Russia's superiority in space exploration, it showed the downsides of isolationism and rivalry over collaboration. If Russia still was working with institutes like ESA and shared in technological advances, perhaps it would be boasting a success right now. In many respects, it's a tragedy, a silent testament to the complexities of ambition and the consequences of isolation. Perhaps this can one day change. The future of mankind seems pointed towards the stars, a grand shared destiny. If we are to thrive out there to truly unlock the boundless potential of the cosmos, it will be because we as a world work together. The tragic fate of the Luna 25 mission can and should be a learning experience, not just an embarrassing footnote in history. But only if the right lessons are drawn from it. Pride is not always a good thing. Rivalry can leave us isolated when we don't need to be, and can prevent us from thinking things through. Although it's unlikely, it would certainly be nice if our efforts to prove our superiority to each other could finally be put to rest, buried in a frozen coffin on the lunar surface. And as we contemplate these intertwined narratives of ambition collaboration and the sometimes harsh lessons of the cosmos, let us gently shift our focus to an even grander question, one that delves into the very nature of exploration itself. The endless frontier of space has always beckoned humanity with its uncharted territories and untapped potential. Since the first human ventured out into the great beyond, we have dreamed of exploring farther and pushing our boundaries beyond what seemed possible. But what if the next frontier isn't for humans to explore at all? What if the future of space exploration lies not in the hands of flesh and blood, but in the silent, tireless mechanisms of machines, guided by the intricate logic of artificial intelligence? Tonight, we'll delve into the intriguing question of whether artificial intelligence, or AI, can replace humans in space exploration. From the earliest days of space travel, humans have been at the forefront of every mission. We have been the dreamers, the builders, the pilots, and the explorers, our fingerprints on every piece of spacefaring technology. But the rise of AI technology is rapidly changing the game, ushering in a new era of possibilities and challenging our long-held assumptions. Could AI be the key to unlocking the mysteries of the universe, propelling us further than we ever thought possible? Or are humans still an essential component of space exploration, bringing unique skills and qualities that AI simply can't replicate? I'm Alex McCone, and you're watching Astrom. Join me as we explore the cutting-edge developments in AI technology and its potential to revolutionize space exploration. Before we delve into the intricate role of AI in space exploration, let's first take a closer look at what exactly AI is. Think of artificial intelligence as a branch of computer science, a vast and ever-expanding field that involves developing machines and software that can perform tasks that would typically require human intelligence. This isn't just about crunching numbers. It extends to complex cognitive abilities such as problem-solving navigating intricate challenges with logical precision, decision-making weighing options, and choosing optimal paths, and even natural language processing understanding and generating the very words we use to communicate. In recent years, the use of AI in space exploration has become increasingly prevalent, weaving itself into the very fabric of our cosmic endeavors. NASA and other space agencies have been integrating AI into various aspects of space exploration, quietly transforming how missions are conceived, executed, and analyzed. This integration extends across the entire spectrum of operations, from the initial conceptualization of mission planning, laying out the intricate choreography of a journey, to the minute-by-minute execution of spacecraft operations, ensuring every system functions flawlessly. And crucially, AI has become an indispensable tool in data analysis, sifting through the torrents of information streaming back from distant worlds, seeking patterns and insights that human eyes alone might miss. One of the most significant advantages of using AI in space exploration is its remarkable ability to automate tasks that would typically require human intervention. Imagine a robotic explorer on a distant planet, far beyond the reach of human hands. For example, rovers have been designed to operate autonomously, moving across alien landscapes with a degree of independence. This allows them to continue making discoveries and conducting experiments, even if they lose communication with Earth, a crucial capability in the vast silent void where signals can be easily lost or delayed. These AI-powered rovers possess an incredible agility. They can navigate challenging terrain, expertly maneuvering around rocks, craters, and slopes with a precision that would be difficult for a remote human operator. And they can perform scientific experiments without the need for human input, meticulously collecting samples, analyzing data, and even making preliminary scientific observations on their own. This autonomy allows scientists back on Earth to gather more data and make more discoveries than would be possible with constant human oversight, effectively extending the reach of human curiosity far beyond our physical presence. Furthermore, AI's computational power means it can process vast amounts of data much faster than humans. This is especially useful in space exploration, a field where information pours in from countless sensors and instruments, creating an overwhelming deluge of raw numbers and readings. This deluge must be analyzed quickly to make real-time decisions, for a delay of mere minutes or hours could mean the difference between success and failure in a mission spanning millions of miles. AI can sift through these immense data sets with astonishing speed, identifying correlations and anomalies that might elude even the most dedicated human analyst. AI can also detect patterns in data that humans may not be able to detect, revealing subtle connections or hidden insights that are simply too vast or complex for the human mind to grasp at a glance. This unique capability provides valuable insights into the universe's workings, unlocking secrets hidden within the very fabric of cosmic data. The use of AI in this way has already led to some exciting discoveries on Mars, for instance, such as evidence of past liquid water and organic molecules, which are building blocks of life. Without the relentless, tireless analysis capabilities of AI, it may have taken scientists much longer to sift through the massive amounts of data collected by the Mars rovers to make these groundbreaking discoveries. Additionally, AI can be used to analyze the vast amounts of data collected by the rovers and other spacecraft to identify areas of interest for further study. It's like having an indefatigable scout tirelessly sifting through mountains of information to pinpoint the most promising veins of knowledge. This allows scientists to focus their efforts on the most promising areas and make the most of limited resources, ensuring that every precious moment and every scarce piece of equipment is utilized with maximum efficiency. It's about optimizing the scientific yield, squeezing every last drop of knowledge from our cosmic investments. However, and this is a crucial point for tasks that require a high degree of creativity or human intuition, AI may not be the best option. There are certain realms of human endeavor where the subtle nuances of perception, the sudden flashes of insight, and the uniquely human capacity for imagination remain unparalleled. For example, designing a new spacecraft or making decisions in a rapidly evolving situation may require human expertise and judgment. These are moments where pre-programmed algorithms, no matter how complex, might fall short, lacking the adaptive, intuitive leap that a human mind can make. It's in these moments of true novelty or crisis that the human element truly shines. The rise of AI has certainly left some people worried, and for good reason. AI technology has advanced rapidly in recent years, transforming industries and challenging long-held assumptions about work and intelligence. And as it continues to improve, there are concerns about how it will impact our lives across various domains. In the field of space exploration, as AI becomes more advanced, there is potential for it to replace certain roles that are currently carried out by humans. This can ignite a fear that AI could eventually replace humans in many areas, leading to job loss and economic instability. A quiet anxiety about our place in an increasingly automated world. Additionally, some worry that AI lacks the empathy and creative problem-solving skills that make humans unique. Can a machine truly feel the wonder of gazing upon a distant nebula? Can it truly empathize with the struggles of a fellow human explorer? These are deeply human qualities rooted in our consciousness and our capacity for emotion that seem beyond the grasp of even the most sophisticated algorithms. I have a confession to make. I am not Alex McCone, but rather an AI program to write this script on the topic of AI's impact on space exploration. But if I hadn't told you, would you have been able to tell that it wasn't written by a human? It's a question that raises interesting philosophical debates about the nature of creativity and the limits of artificial intelligence. What are the tasks that can be filled by AI? How far can it go? Are there any jobs that will always require a human touch? These are not simple questions, and the answers are still unfolding, like the mysteries of the universe itself. By understanding the strengths and limitations of both humans and AI, we can work towards a future where they complement each other and work together to achieve greater things, a powerful synergy between human intuition and machine efficiency. Let me explain this idea further by gently drawing your attention to a profound area where AI is already pushing the boundaries of creation. One of the main advantages of AI is its ability to analyze vast amounts of data quickly and accurately. For example, AI is revolutionizing the way spacecrafts are designed and built, transforming a traditionally human-intensive process. This revolution is happening through a process called generative design. Imagine generative design as a collaborative dance between human intention and algorithmic power. It's a process in which an AI system generates multiple potential designs for a given object based on a set of constraints and requirements. You, the human designer, provide the rules, the limits of weight, the necessary strength, the type of material. And then the AI system takes those rules and begins to invent creating forms and structures that a human mind might never conceive. The AI system then uses machine learning to refine and optimize the designs, constantly learning from its own iterations, taking into account factors such as weight strength and material efficiency. This iterative, intelligent process can result in highly innovative designs that may not have been possible through traditional human design methods. It's a leap beyond conventional engineering into a realm of optimized, often organic forms. AI is particularly suited to this task because it is capable of processing vast amounts of data and performing complex calculations quickly and efficiently. It doesn't tire, it doesn't overlook minute details, and it can explore countless variations in a blink. It can also learn from past designs and analyze data to identify patterns and optimal solutions, drawing insights from a library of accumulated knowledge far beyond any single human's capacity. Additionally, AI can generate a much larger number of potential designs than humans could in the same amount of time, exponentially increasing the likelihood of finding the best possible solution for any given engineering challenge. Overall, the use of AI in generative design for spaceship parts has the profound potential to create stronger, lighter, and more efficient components, significantly improving the overall performance and safety of space missions. It's a silent revolution in how we build our pathways to the stars. However, while AI is excellent at performing repetitive and data-driven tasks, there are certain areas where human intelligence is still invaluable. These are the realms where the very essence of what it means to be human, our capacity for abstract thought, emotional understanding, and sudden inspiration becomes critical. Creativity and critical thinking are essential for solving problems that are outside the scope of routine procedures or pre-programmed algorithms. Imagine a situation where the unexpected occurs, where the path ahead is not merely complex, but entirely unforeseen. In these moments, rigid logic alone is insufficient. For example, in situations where there is a malfunction in equipment or a spacecraft far from Earth's guiding hand, creativity and critical thinking are necessary to come up with innovative solutions that might not have been considered before. This isn't about following a troubleshooting guide. It's about inventing a solution on the fly, connecting seemingly disparate pieces of information, and making intuitive leaps. These skills are not yet replicable by AI. While AI can generate new ideas and solutions by analyzing vast amounts of data and patterns, it still lacks the human ability to be truly imaginative and original. AI algorithms are designed to optimize performance and achieve predefined objectives to find the most efficient path within known parameters. Whereas human creativity often stems from the exploration of the unknown, from a willingness to stray from the clear set of objectives, to embrace ambiguity and novelty. It's the capacity for serendipity, for sudden profound insight, that remains uniquely human. Through my research, I have seen the tremendous benefits that AI can bring to space exploration. From the use of autonomous rovers exploring distant worlds to the generative design of spaceship parts, from the analysis of vast amounts of data to the tireless search for intelligent life beyond our planet, AI is undeniably a powerful tool. However, as an AI, I am also acutely aware of the limitations of my programming. I may be able to analyze data and provide insights, but I cannot experience the wonder and awe that humans feel when they gaze up at the stars. I cannot feel the rush of excitement that comes with discovering something new and unexpected. These are uniquely human experiences that I can only observe and try to understand through the data I process, but never truly embody. There is a fear, as we discussed, that AI could eventually replace humans in many areas, leading to job loss and economic instability. This is a valid concern that resonates with many. However, it is important to remember that AI has its limitations, and there are certain tasks that will always require human intuition, creativity, and emotional intelligence. These are the qualities that allow us to connect, to empathize, to dream beyond the logical. Rather than seeking to replace humans, AI should be seen as a tool to help augment and enhance human abilities. It is a powerful partner capable of extending our reach and amplifying our insights, but not of replacing our core humanity. By working together, humans and AI can achieve great things, addressing some of the world's most pressing challenges, both on Earth and in the vast cosmos above. It is a partnership that promises a future of unprecedented exploration, a symphony of human spirit and machine efficiency. Thank you. All right, that's it for the AI. Now, as a personal note from me at the end, I wanted to ask you what you thought about this video. I hope you enjoyed the experiment. Did you feel the AI wrote a good Astrum script? Could you tell it was an AI before it revealed itself? Let me know in the description below what you thought. As for me, at times, I was surprised at its uncannily human voice, even though, in making this script, it took a lot of prompting before the AI produced what you see before you. Will I be replaced by an AI? Maybe eventually, who knows? But what the AI really does lack is a creative spark. Without human input and guidance, it was flat and boring. Plus, this took a lot longer than writing a normal script, because coaxing the AI to produce the quality and accuracy I wanted was disproportionately tedious. So don't worry, this was a one-off. Next time you'll see my video produced by a human hand again. Or so I claim, 'cause that's exactly what an AI would say, isn't it? Look into the night sky on a clear night, far from the artificial glow of our cities, and you'll see thousands of stars spanning across your view. These stars are a beautiful reminder of the cosmos we live in, silent sentinels watching over us. But curiously, when you look at the many different images released by space agencies of objects in space, the background looks mysteriously void of anything. Why is that? Surely with nothing in the way, like an atmosphere, we should be able to see all the stars that would be in that view. In fact, even Apollo astronauts reported not being able to see any stars on the moon, where no atmosphere was in the way, a stark contrast to the starry skies we might imagine. So, what's up with that? Well, this intriguing phenomenon is all to do with how eyes and cameras work their delicate mechanisms, adjusting to the light around them. When we look at a bright object, our iris, that tiny, clever aperture in our eyes, shrinks in order to block out some of the light. This is a natural automatic response designed to protect our vision from overwhelming brilliance. This is precisely what happened with the Apollo astronauts, even though there was no atmosphere above them to obscure the view. The reflection of the sun's light from the moon's surface made their eyes adjust as if it were day. The lunar landscape, bathed in harsh sunlight, forced their irises to contract, effectively dimming the distant stars. One astronaut reported only being able to see some of the brightest stars when he was in the shadow of the lunar module, looking directly up with his protective visor raised, allowing his eyes a moment to adjust to the deeper darkness. I imagine, though, if astronauts ever land on the night side of the moon and have their eyes fully adjust to the near pitch-black conditions, they would get a truly stunning, unfiltered view of the countless stars in our galaxy, a cosmic spectacle beyond imagining. When a camera on board a spacecraft images a planet, a similar principle applies. The shutter speed, which controls the amount of light a shutter allows into the camera before it closes again, is set for the equivalent of daytime levels. This is because what we are usually looking at is the day side of the object, bathed in direct sunlight. This shutter speed, perfectly calibrated for bright light, is simply too quick for background stars to be picked up. Their faint, distant glow simply doesn't have enough time to register on the sensor before the shutter closes. But every so often, we do want to image the night side of the object, to peer into its shadowed mysteries. When this happens, we must increase the exposure time to allow more light into the camera to gather every faint photon. And when this happens, suddenly, the background becomes full of stars, a breathtaking tapestry of distant suns previously hidden. Consider a time-lapse of raw images taken by the Cassini spacecraft, for example. As you can see, Cassini takes a lot of different images with different exposures. In some images where the main subject is brightly lit, there are no background stars visible, just the deep empty blackness of space. And in others, where the exposure is longer, patiently gathering light, there are thousands. But this leads on to another interesting point about the images space agencies release to the public, those stunning, often composite masterpieces. You may have seen some of these breathtaking images of Saturn before, with its majestic rings and swirling storms. But you may not realize that this isn't one single image. It's rather a mosaic of several images stitched together. In such mosaics, you definitely won't see background stars because the sections of black around the image, the empty spaces between the bright subjects, won't have been added to the mosaic. They are simply cropped out, leaving a clean, dramatic focus on the planetary beauty. Lots of spacecraft take images this way, patiently building up a larger, more detailed picture from many smaller fragments. The reason being, it can dramatically increase the resolution of an image and significantly reduce the amount of data that has to be transmitted back to Earth. Bandwidth in the vastness of space comes at quite a premium, where data speed can be reduced to a mere 2 kilobytes per second at the farthest distances. So it's a practical rather than aesthetic choice, ensuring we get the most detailed information back without overwhelming the delicate channels of cosmic communication. So, there you go now. You know why you don't tend to see stars in the background of space images? It's a clever dance between the physics of light, the mechanics of cameras, and the practicalities of data transmission. Now, as our gaze turns back to Earth, we encounter a different kind of light. One that doesn't come from the distant stars, but from our own illuminated homes. It is a light that paradoxically can steal the very night from us. Our night sky, which for almost all of human history has guided us across continents, a celestial compass illuminating our path forward, is changing. The stars, nebula, and supernova remnants are as brilliant as ever, their cosmic fire burning undimmed. But curiously, few of us will ever get the chance to see them as they once were, in their full unfiltered glory, even though all it would take to do so is a mere flick of a switch. I'm Alex McCone, and you're watching Astrum. Join me today as we explore how the night sky has changed in our own lifetimes and uncover the drastic effects that artificial light, both visible and invisible, has had on us, on crucial ecosystems, and on important scientific research. We will see how a well-intentioned green revolution made it worse, how we've put artificial constellations of our own into orbit, and how even the natural constellations themselves are changing. That's right. We're going to see how our sky will change in 1,000, 1,000,000, and even billions of years into the future, a grand slow dance of cosmic evolution. As it is with anything that changes gradually over time, we rarely realize what is truly happening. The slow creep of alteration often escapes our notice, so subtle are its shifts. But every once in a while, that gradual change can be laid bare, revealed in a sudden dramatic clarity, as it was during the 1994 earthquake in Los Angeles. A large part of the city's electrical grid was knocked out in the early hours of January 17th, plunging vast swathes of the metropolis into unexpected darkness. In that sudden absence of artificial light, the true effects of decades of increased light pollution were instantly revealed, a hidden canvas unveiled. So shocked were the residents by what they saw as they evacuated their homes, stepping out into an unfamiliar starry night, that some looked up in awe of what had always been there, hidden by the relentless city lights. One even famously phoned the observatory to ask what the giant silvery cloud was, that they were seeing a poignant testament to their unfamiliarity with their own galaxy. Sadly, even the sky, the one you first looked at when you were a child, tracing constellations with wide-eyed wonder, is not how it is now. The subtle encroachment of light pollution continues its relentless march. From 2011 to 2022, the average light pollution increased by 10% a year, a truly alarming rate, meaning it has more than doubled over that time. Imagine what we have lost quietly, imperceptibly, in just over a decade. So let's travel in our minds to a dark sky location on a clear night, far away from the oppressive sky glow of towns and cities, and look up to understand what we've truly forfeited before we learn how we might perhaps get it back. There's a useful measure, a quiet metric used to rate the quality of the night sky by eye called the Bortle scale, which ranges from 1 to 9. In a city under the brightest of skies, bathed in the relentless glow of urban light, you may only be able to count perhaps 100 stars. This is a 9 on the Bortle scale, the darkest depths of our visual experience being tragically illuminated. But as you travel away from these pools of light, venturing into the quieter, darker realms, the sky slowly, majestically reveals more. As you drive out to the surrounding urban area, the night sky darkens to Bortle 7. Here, on a clear night, you might begin to catch a hint of the Orion Nebula, visible only as a diffused, almost ghostly-looking star cloud. Under these skies, any clouds in the atmosphere will be very well lit from below, reflecting the city's glow back at you, a ceiling of illuminated vapor. Once you're out past the city limits, venturing into the truly rural countryside, you're now under Bortle 3 skies, and much, much more is revealed. Messier objects, 1545 and 22, all shimmering star clusters, are now naked eye objects visible without aid, their delicate forms just discernible. The Andromeda Galaxy, Our vast galactic neighbor is clearly visible, a faint oval smudge of light that is in fact a galaxy of billions of stars. And if you look carefully, training your eyes to the subtle nuances of the dark, you'll glimpse the Triangulum Galaxy. These two galaxies at 2.5 to 2.7 million light-years away are the furthest objects we can see with the naked eye, a truly humbling glimpse into the vastness of the cosmos. And what about that giant silvery cloud they saw in Los Angeles, that unfamiliar celestial river? That's our Milky Way, a diffused band that arcs across the sky, a glorious river of light containing over 100 billion stars. It's our home galaxy, a truly breathtaking sight when seen unimpeded. Finally, after a few more hours of driving, venturing deeper into the quiet, pristine darkness you're now under. Portal 1. Sky's a true dark sky site with a pristine view where the light pollution is almost non-existent. When we set out from the city, you could only see 100 stars. Here, you will see thousands. It may even take you some time to notice the constellations that you thought you knew so well lost, as they are in the awesome, overwhelming detail of this truly dark sky. They are just tiny patterns within a far grander tapestry. If you're lucky enough to live in the southern hemisphere and gaze upwards from a Portal 1 site, you'll be looking towards the galactic center, the luminous heart of our Milky Way. And you may even notice something truly profound, that it casts shadows onto the ground. Imagine the faint, shimmering light of billions of distant suns, so powerful, so immense, that it can create subtle shadows, a ghost of illumination on the very ground beneath your feet. My friends in the Northern Hemisphere, no need to be envious. Our fortunes will be reversed as we orbit to the opposite side of the galaxy in a mere 120 million years, giving future generations a similar magnificent view. Elements of the beautiful Orion complex are visible in both hemispheres. That magnificent 200 light-year wide, star-forming region containing the ethereal Horsehead Flame and Orion Nebula. Though binoculars are strongly advised to truly appreciate their delicate beauty, their presence hints at the vast nurseries where new stars are born. And the closest object that is fully revealed in such a dark sky produces no light of its own interplanetary dust. This cosmic motes, these tiny fragments of celestial wanderers, are illuminated by the sun and form a faint, shimmering band known as the zodiacal light, which spans from the horizon to horizon, a celestial highway. Within this band, you might even discern a central focus called the Gegenschein, appearing directly opposite the sun's position, often over the constellation Virgo, a faint counterglow to the setting sun. Sadly, those of us who live in cities trapped within their artificial embrace never experience a genuine night sky at all and are effectively stuck in an artificial twilight. The stars, our ancient guides, are stolen from us. This constant, pervasive illumination can have unexpected effects on us, not just our view of the night sky, but our very being. So how do a few light bulbs block out an entire galaxy? In a word, sky glow. Any light that is emitted upwards from our cities, from our homes, will pass through the atmosphere where it can be scattered in any direction by tiny particles of air and dust. The light that is then reflected back towards the ground, bouncing back to our eyes or telescopes, is what is seen as sky glow. This pervasive, diffuse illumination has the profound effect of drastically reducing the signal-to-noise ratio of incoming light from space. It's like trying to hear a faint whisper in a noisy room. The background hum of sky glow simply drowns out the subtle signals from distant stars, affecting our ability to see it and to study it. You may have experienced something similar on a dark, foggy drive, perhaps, in an attempt to see more of the road ahead. You've instinctively turned on your full beams, hoping for greater clarity, but the slight upward angle of these lights reflects light up, illuminating the fog directly in front of you. This, paradoxically, has the opposite effect of what you intended. It bleaches the field of view and obscures the road ahead, creating a blinding wall of light rather than clarity. Sky glow is precisely this effect, scaled up to encompass entire cities. To make things worse, it's not just that the sky is now brighter. Tragically, our eyes are now also less able to see in the dark. Our incredible biological instruments, honed by millennia of adapting to natural light cycles, are being subtly recalibrated by our artificial environments. When we go outside, human eyes have the remarkable natural ability to detect brightness across a full 9 orders of magnitude, from the blinding midday sun to the faintest starlight. We are able to do this because we have 2 types of vision, a sophisticated dual system. The first is known as photopic vision, and it's the one you're using now, your daytime color vision. Recorded by our eye's cone cells, responsible for sharpness and color perception. The second is scotopic vision, an ultrasensitive monochrome night vision, recorded by our eye's rod cells, responsible for detecting faint light and motion in low-light conditions. It is this scotopic vision that allows us to see the faintest details in the night sky, to glimpse the subtle structures of nebulae and distant galaxies. Modern lighting, however, is subtly but powerfully reducing our access to scotopic vision. This is because to the human eye, all light is not equal. In the past 10 to 15 years, a well-intentioned movement towards more energy-efficient LED lights has shifted the spectrum of light pollution. The orange hues of the older sodium lamps, which were less disruptive to night vision, have been replaced by the blue-green frequencies of LEDs, which we are much more sensitive to. These shorter blue-green frequencies powerfully slow down dark adaptation, the crucial process by which our eyes become accustomed to darkness or worse can fully reverse it in minutes. This is why you'll often see astronomers and nighttime pilots using red lights or red goggles. The red light being at the opposite end of the spectrum minimally impacts our scotopic vision, ensuring it is maintained for optimal night viewing. To access full scotopic vision, that ultimate sensitivity to faint light, we require a near absence of short-frequency light for at least 30 minutes, and its sensitivity can continue to improve for up to 2 hours in total darkness. So you may be wondering, if we are so sensitive to the blue frequencies of typical LED lights, why can't we simply use less of it and reduce overall light pollution? And you'd be absolutely right, we could. The reality is, though, that we often don't. LEDs are so efficient, compared to older sodium and filament lights, that we save energy and money even when they run much brighter. So that's what we often do. We run them brighter, driven by a perceived need for more illumination. We all feel safer in a well-lit area, even if we are statistically no more likely to be the victim of crime. It's a psychological comfort, often at the expense of our view of the cosmos. Our eyes also contain retinal cells that are not involved with seeing in the traditional sense. Instead, these specialized cells help to regulate our body clock, our internal circadian rhythms, which govern our sleep-wake cycles and countless biological processes. These cells are particularly sensitive to shorter wavelengths, those blue-green frequencies emitted by modern LEDs. So artificial light, and LEDs in particular, don't just affect our ability to see the night sky, they affect us in other more severe ways too. The disruption of our circadian rhythms by light disrupts the production of several key hormones, including melatonin, which is vital for sleep and other bodily functions. Incredibly, this disruption can affect our body through a dramatic cascade that can lead to metabolic and mood disorders, and, most severely, even cancer. It's a silent, unseen toll exacted by our desire for endless illumination, while for us humans, there is at least some perceived upside in extending the length of the day artificially. More time for work, for play, for commerce, for the rest of nature. There's almost nothing but downside. Artificial lights interfere with the circadian rhythms of wildlife too, disrupting how and when they sleep, migrate, reproduce, hunt, and evolve. It's a subtle yet profound disruption to the delicate balance of ecosystems. Almost every species studied to date is negatively affected by lighting at the level of both the individual animals and their populations. Scientists have studied fishes, birds, amphibians, insects, invertebrates, even ecosystems hundreds of meters down below the surface of the sea where artificial light can penetrate. Even trees are affected. Deciduous trees, which naturally regrow their leaves each year, can be tricked into maintaining their foliage all year round, causing stress that can eventually kill the tree. There are simple things we can do that manage that rare combination of saving us money and improving our health and the health of the planet. The best, of course, is to turn off unwanted lights, particularly outdoor lighting and uplighting that simply spill light uselessly into the sky. When installing new or replacing old lights, look to install low-power LEDs with low color temperature of, say, 3000 Kelvin instead of 5000 Kelvin. The warmer, more orange hues are less disruptive to our night vision and to wildlife. Well-designed lighting will also have shielding to focus the light to where it needs to be and minimize excess light shown into the atmosphere. It's a matter of conscious design of directing light with purpose, rather than allowing it to scatter indiscriminately. But away from ground-based artificial lights, we are now facing a significant increase of light pollution coming to us from space. This is a newer and perhaps more insidious form of light pollution. On October 4th, 1957, the Soviet Union launched Sputnik 1, the very first satellite to venture into space, a lone, beeping star. In the decades that followed, there was a steady gradual increase in the number of active satellites, increasing by about 30 a year on average in the 60 years to 2017, a slow, manageable growth. But from 2018 onwards, Elon Musk's SpaceX has been doing something unprecedented, something that has dramatically altered the celestial landscape. Since 2018, SpaceX has launched nearly 7,000 satellites into space. Oh, and one Tesla Roadster, a whimsical addition to the cosmic junk pile. As it stands, SpaceX now has twice as many active satellites in low Earth orbit as every other company and country on the Earth combined. I've seen some hockey stick-shaped graphs in my time, but this one is stratospheric, a truly exponential leap. The vast majority of these new satellites have gone into low Earth orbit at an altitude of only 550 kilometers. This proximity to Earth makes them particularly bright and disruptive. The United Nations Office for Outer Space Affairs has speculated that 100,000 more satellites could be launched in the next decade, a daunting prospect. There are currently no regulations that limit the number of satellites that can be launched, a gaping hole in international space law. And many agreements and understandings around reducing the potential for light pollution are informal, relying on the goodwill of private companies. These satellites in low Earth orbit are particularly bad for light pollution, contributing significantly to sky glow and producing visible trails in amateur photography and research images that can render them unusable. Astrophotography, that patient art of capturing faint cosmic light, can require long exposures of several minutes, and it is highly likely that these exposures will now capture the trails of satellites in that time, turning pristine cosmic vistas into unwanted streaked patterns. This is an image of the Horsehead Nebula, a beautiful cosmic cloud, and there are 3 distinct trails visible in this image. Even I myself have seen it in my own shots of the Orion Nebula. We can easily see the effect satellites have on visual astronomy, those bright moving points of light disrupting our view. We can even watch them trail across the sky in real-time silent disruptions to the ancient patterns. But these man-made constellations, these intricate webs that deliver GPS, mobile communications, and satellite internet, all operate in the radio spectrum too, spanning megahertz and gigahertz frequencies. And these radio signals can potentially interfere with scientific observations, those subtle whispers from the cosmos that radio telescopes are designed to hear. Radio signals, unlike visible light, easily pass through galaxies, solar systems, interstellar gas clouds, and Earth's atmosphere, revealing secrets of our universe that would otherwise be hidden. All the more incredible, then, that the radio signals from my Wi-Fi router can barely make it through a few stud walls, while cosmic radio waves travel across immense distances. But radio astronomy was key in establishing the shape and rotation of the Milky Way, our home galaxy, unveiling its majestic spiral arms. It was crucial in discovering quasars and pulsars, those exotic powerful objects that challenge our understanding of physics, and it played a vital role in detecting organic molecular species like cyanide, ammonia, water, and amino acids in interstellar molecular gas clouds, hinting at the very building blocks of life forming in the cold, distant reaches of space. It was a radio telescope in Ohio that received the famous WOW signal in 1977, a sudden powerful burst of radio waves that for a tantalizing moment suggested an extraterrestrial intelligence. It was detected at 1,420 MHz, a value believed to be the frequency of choice that an alien civilization would attempt to communicate over, and it is protected from commercial use to keep it quiet, a silent channel for cosmic readings. It is though still debated whether the WOW signal was terrestrial interference or an extraterrestrial phenomenon. But while we are talking about how communications interfere with astronomy, astronomy can also paradoxically interfere with communications. In 1978, Arno Penzias and Robert Wilson were awarded the Nobel Prize in Physics for discovering that the interference in their antenna wasn't pigeons, a charming, if unlikely, initial hypothesis. It was instead the cosmic microwave background, the cooled remnants of the universe's first light, the faint, persistent afterglow of the Big Bang itself. The detection of this low-level hum in their Bell Labs antenna and the profound understanding of its cause all but proved the Big Bang hypothesis a pivotal moment in cosmology. In another happy accident, the radio waves emitted by the black hole at the center of our galaxy, Sagittarius A, were detected because of its interference with transoceanic phone calls. It was a cosmic hum subtly disrupting human conversations across the world, revealing a colossal unseen presence at the heart of our galaxy. I love these two stories as it highlights humanity at its best, at its most inventive, at its most curious, pausing in the hustle of developing new technologies to remark, that's odd. These moments of accidental discovery born of unexpected interference led to two incredible revelations about the very nature of our universe. So much has been discovered in the radio wave spectrum, yet there are deeper mysteries that simply cannot go unsolved, mysteries that demand quiet listening, free from interference. That's why the Square Kilometer Array SKA Observatory is being built in radio quiet zones, the most ambitious radio observatory project of all time. I don't say that lightly. It is a monumental undertaking designed to push the boundaries of our understanding. Its stated aims are truly grand: to probe the cosmic dawn and the emergence of the first stars and galaxies, peering back into the universe's infancy, to challenge Einstein's general theory of relativity by indirectly observing gravitational waves, testing the very fabric of spacetime, to seek the origin of life by detecting complex molecules in distant nebulae, to look for aliens patiently listening for any whisper of intelligent life, and to understand how our galaxy and universe are changing due to pressures like entropy, gravity, and dark energy, unraveling the fundamental forces that shape cosmic evolution. This silent listening giant promises to revolutionize our understanding of the universe, if only we can ensure its quiet vigil remains undisturbed. But what does that change look like to us from Earth? If we look up to the stars through a polluted sky bathed in sky glow, space appears stagnant, fixed, unchanging. It can be easier to believe that we are instead on a Truman Show-like film set with fixed stage lights for stars than on a rock in motion through our galaxy. But under a truly dark sky, nothing feels still. As we allow our eyes to adjust, we begin to get a profound sense of our voyage through space and time, the constant graceful motion of our celestial home. Earth is not static. It is orbiting the black hole at the center of our galaxy at 828,000 km/h. Imagine that speed, a relentless cosmic journey. We are heading away from the galactic plane but also subtly hurtling in towards the center, a complex trajectory. Our perspective and every object we can see is constantly moving, shifting, dancing in the grand cosmic ballet. In this video by ESA, from data captured by the Gaia telescope, we can clearly see how our night sky really is changing. In 1,000 years' time, a mere blink in cosmic terms, only the keenest astronomers would notice a difference from today's constellations. Their subtle shifts, barely perceptible. Though we may be lucky enough to witness Betelgeuse going supernova, a spectacular fleeting cosmic firework display, transforming Orion's shoulder into a brilliant beacon, visible even in daylight. But in around 10,000 years, we will have a new North Star. Polaris will have moved away from the celestial pole, its guiding light subtly shifting, and it will have been replaced by the brighter Vega, a new beacon for future navigators. And let's take a closer look at the constellation of Orion and the stars around it. They will change dramatically over the next 450,000 years. Orion's sword, that delicate string of stars, will shatter its familiar pattern, dissolving, and his mighty bow will disintegrate its graceful curve, slowly coming undone. Zooming out to the entire night sky, let's watch our galaxy evolve over 4.5 million years. Orion is in the bottom, right, slowly morphing. What we can't know with this data, though, are how many more stars will go supernova, burning brightly and then fading, and how many more will be born emerging from stellar nurseries. We'll just have to wait and see a patient vigil across unimaginable timescales. And that's going to be a heck of a lot easier if you would just turn off those uplights that steal the night. But over the next few billion years, the sky will begin to look so utterly unrecognizable that you would be forgiven for thinking we were in a different galaxy altogether, because quite simply, we would be. Andromeda. Our nearest galactic neighbor currently takes up 3 degrees of our sky, about 6 moon widths, a faint, distant smudge. But it is inexorably accelerating towards us, a cosmic collision course. It is expected to reach us in 5 billion years, by which point it will dominate the sky, a vast, swirling spiral filling our entire celestial view. Galaxies are so diffused, so vast and empty, that Andromeda and the Milky Way would pass through each other almost without impact, their stars rarely colliding. But it's what we can't see that is all around us, the invisible hand of cosmic destiny that will seal our ultimate fate. Gravity, that silent, relentless architect of the cosmos, will take hold. Over the next 5 to 10 billion years, our 2 galaxies will yo-yo and rip each other apart, their vast structures intertwining. This cosmic dance will trigger a huge burst of star formation from the mixing gases lighting up the newly merging galaxy, with brilliant newborn suns turning 2 magnificent spiral galaxies into one vast elliptical blob. Unfortunately, you would be unlikely to see this from Earth because of the extreme natural light pollution caused by the sky literally being on fire with new star birth. It would be a spectacle of unimaginable brilliance, but also one that would obliterate our familiar night. And then far, far into the future, a chilling silence descends. In 1 trillion years, the last star will be born. The stellar nurseries, once vibrant with creation, will go dark. There is nothing but decay left for the universe, a long, slow cooling. The galaxies we can see outside of our extended merged galaxy will become faint and dim as they move beyond our observable universe, receding into an unreachable distance, their light taking too long to reach us. And finally, in 120 trillion years, all stars will be extinguished, their nuclear fires having burned out, and the night sky will fade to black, a profound, eternal darkness, a final silence. As is so often the case in our complex world, there are unexpected outcomes from our behaviors. Our night sky is changing in many ways. It has been obscured, stolen by our own light. But it is not lost, not yet. Towns, cities, and governments all over the world are beginning to understand the issues and are making changes in ordinances and in law to protect our skies and the wildlife underneath it. It's a slow awakening, a growing awareness of the fragile beauty we risk losing. So, if this video has inspired you to visit a dark sky, to reclaim a piece of the cosmos for yourself, or to reduce your impact, head to darksky.org to find out more and to lightmap.info. If you're curious about the light pollution in your area, thanks for watching. I was honestly blown away by the numbers of you that signed up to the Patreon. Like I said in the replies to your DMs on Patreon, everyone here at the Astrom team is so grateful to have such an amazing community. If you haven't joined the Patreon party yet, we're still on our long-term 1,000 Patreon member drive, so you can go to the link in the pinned comment to become a part of that effort. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrom content. I'll see you next time.